Assalamu alaikum. Hello, everyone. Thank you so much for joining us as we welcome our third speaker for the second edition of the AI Summit. Today's guest is very special with a very special topic. So welcome again, Professor Onur Mutlu. Professor Onur Mutlu is Professor Onur Mutlu is a professor of computer science at ETH Zurich, a faculty member at Carnegie Mellon University, and a visiting professor at Stanford University. Professor Onur Mutlu led several research positions in academia and industry. He is the Safari Research Group leader at ETH Zurich and the founder of the Computer Architecture Research Group at Microsoft. He also led other several research positions at Intel, AMD, Google, and VMware. He made several contributions that shaped the design of modern high-performance processor. And today's talk is going to be about a very interesting topic, which is relevant to all fields of applications. It's memory-centric computing. So welcome again, Professor Onur Mutlu, and the stage is yours.
Okay, thank you. Thank you very much, Ramzi, and thanks for the invitation and introduction. I'm going to switch to my slide sharing. You can hear me well, right? Everything is good? Okay, I am assuming that everything is good, so I'll continue. So welcome, everyone. I'm going to talk about memory-centric computing today. This is an area that's becoming a lot more important going into the future, and hopefully we'll have a good discussion. So if there are any questions at any point in time, please ask, and I think Ramzi can interrupt me. The only thing I see right now on my screen is my slides, so chat won't work. Okay, so let's dive in. So today, if you look at computing, it's really bottlenecked by data, mainly because important workloads are all data intensive. If you look at machine learning, for example, artificial intelligence, robotics, genomics, these workloads require rapid and efficient processing of large amounts of data. And we're actually creating other workloads that are going to require even more processing, as I will mention soon. And on top of this, data is increasing. We can generate more data than we can process in many domains. And we also need to perform more sophisticated analyses on more data so that we can actually achieve some of the goals or to solve some of the interesting problems that we want to solve. This is just one example. Neural networks clearly have been growing significantly. Machine learning in general, these days it's large transformer models like GPT, etc. But if you look at this picture over here, memory requirements of the models are growing exponentially, and the compute requirements of the models are also growing exponentially. And this is a slide from the Cerebras chief architect, Sean Lee. He was invited for a talk that we hosted on YouTube. You can find the talk over here. But basically, these folks are building wafer scale chips that are this large, so that they can put lots of compute and memory together, which is kind of in line with what I'm going to talk about, but we're going to be a little bit more aggressive in terms of how we can combine memory and compute together in this talk. So essentially, neural networks are an interesting application, and a lot of people are clearly working on it, and it's an exciting area, but they're not the only application. There are many, many other applications that require this large memory systems and also compute requirements at the same time, databases, graph analytics, different kinds of data analytics and data center workloads. All of these are really bottlenecked by data. Performance and energy efficiency is really bottlenecked by the data that we process. And on the mobile end, we also have similarly bottlenecked applications. I'm going to talk about these later on. But for example, inference at the edge, machine learning inference, machine learning training at the edge is bottlenecked by data again. Video is another example. And you can come up with many, many other examples. I'm going to spend a few minutes to talk about a special application. I think there are many, many interesting application domains in the world, but genomics is very interesting because this is an area where technology has created a huge data problem. Basically, we have been able to create these genome sequencing engines. I'm going to show you some pictures later on about these. Essentially, because of the success of how fast we can sequence genomes and the cost of sequencing genomes, the cost of sequencing genomes has been reducing exponentially, greatly, in this, as indicated by this curve over here. I hope you can see my cursor. And with the introduction of new technologies, this cost of genome sequencing has been reducing even more. And this is compared to the cost of a transistor over here, which is reducing exponentially, but at a much lower exponent than the cost of genome sequencing. This means that we can generate a lot more data, genomic data, than we can put transistors on a particular chip. This means that we clearly have a computation problem, mismatch between the data amount and the computation capability. And genome sequencing is interesting. This is one example of the sequencing device. Basically, it creates a lot of reads, and then you need to do a lot of computational analyses to understand what those reads mean and what they mean at a higher level in terms of a scientific level or a medical level, for example. And again, we're bottlenecked by performance energy. I won't go into a lot of detail on these problems, but clearly, genome analysis is important for many, many things, for science, medicine, and also dealing with outbreaks like COVID-19, for example, and also developing personalized medicine. So there are many applications over here. And in the end, we're bottlenecked by data. I'll show you one particular machine that we've been working a lot with. This is the nanopore sequencing machine. Basically, this is a small device. You can buy it for relatively cheap, comparatively. It's about $1,000 or so. And this device can generate genomic data at a very high throughput, reasonably low latency. Unfortunately, this device has no intelligence associated with it, meaning it cannot do any analysis on the data. In order to do something about this genomic data, you need to move that data, usually to a data center, to do some processing and to do comparisons to other genomes, for example, so that you can answer a medical question. And in some cases, for example, this is not good because the analysis takes a long time and the data movement takes a long time. As a result, you waste a lot of energy. And in some latency critical cases, for example, if you have a critically ill patient, a baby, for example, you may actually have issues in terms of how fast you can do the processing. So you can see that this simple machine can generate a lot of data over here. And this is the kind of the problem that we have in many domains. And in this particular case, we want to put a lot of intelligence to this machine so that we can do the processing on site, so that we can take actions relatively quickly. Of course, we're not there yet, and I think this is kind of our dream, but this requires putting compute, memory, and computation in memory together at a macro scale as well as a micro scale, as we will discuss. For the rest of this talk, I'm going to talk a lot about the micro scale. Let me generalize the problem a little bit. So I've shown you this machine. This is the Illumina genome sequence analysis sequencing machine. Basically, this is a special purpose machine that can generate data really fast. It's specialized. And then what we do is we move the data, we cause a lot of data movement out of these machines, and feed it to a general purpose machine for data analysis. So we have a mismatch over here, but this general purpose machine is not specialized for the data that we're generating. As a result, it's slow. So our processing capability is slow and inefficient. And we also cause large amounts of data movement in the system. This is the problem that we want to solve in the end. We want to make our systems very specialized to the types of data that's being generated and to the types of analyses that is being done. And also, we want to minimize the data movement as much as possible. And this picture is actually similar for many data generators and analyzers today. You can replace this genome sequence analysis machine with another nanopore sequencer, for example, or an array of nanopore sequencers, or you can replace it with video, an array of video devices, for example, video cameras all over the world. You can replace it with clicks on the web. You can basically pick any of the interesting application, and they're all data intensive in the end. And we all have this problem in all of those applications. Okay, I'm not going to talk a lot more about genome analysis. It's a special topic that my research group works on, and we do a lot of interesting things. I'll refer you to some papers. This is one example paper that summarizes what we have done. This is another example paper that also summarizes that we've done. And if you're interested in a longer summary, this is a reasonably long summary that talks about what we can do with genome analysis and how we can make it more intelligent, including how we can design intelligent architectures as well as intelligent algorithms so that we maximize the efficiency of processing as well as maximize the performance. Now, I'll tell you what we can do today. So today, we have reconfigurable architectures like FPGAs, and you can actually couple these reconfigurable architectures with high bandwidth memory. So you can actually take a general purpose CPU with some good interface. Today, it's going to be CXL going into the future. I'm going to mention that, but OCAPI is an early version of CXL. This interface enables you to offload computation to a device relatively easily with some coherence mechanisms, for example. And this board you can buy today. It has an FPGA reconfigurable architecture, and this FPGA is near memory, meaning it has very high bandwidth connections to a high bandwidth memory, HBM that's also on the board. And this way, you can actually have specialize the computation to the application that you're offloading to this board. And also, you can enable high data movement bandwidth through the HBM. So what we did was we actually worked with IBM to investigate the benefits of this sort of technology. And we adapted weather modeling, Cosmo weather modeling application, and some genome analysis application so that we can actually perform offloading to this FPGA board, and we can do efficient processing. And the results are actually quite good. And you can actually do this today with some pain, of course. You need to program the application such that you can reconfigure the logic to the key parts of the application and also maximize the bandwidth coming from high bandwidth memory. It's not easy, but it's doable. And as a result, you gain significant performance energy efficiency improvements that are depicted over here. I will not go into detail, but genome analysis application gets accelerated significantly, and so does the weather or climate modeling application. So clearly, we can achieve a lot today with this sort of architecture. And this sort of architecture is actually a near memory acceleration engine, similar to what I'm going to talk about. But in this talk, hopefully, I will motivate everyone to look into even more aggressive in-memory acceleration mechanisms. And we're going to talk about them. We're going to classify them, etc. And again, there are other examples of this that are not doable today. You can design the algorithm and the architecture together so that you can do near memory acceleration for approximate string matching, for example. These are papers that we've written on the topic. I'm not going to go into the details of any of them, but people can read them and discuss them. If you have any questions, feel free to reach out. You can actually do this on, you can adapt some of these algorithms to existing CPUs, GPUs, and ASICs. You don't have to do them near memory necessarily, and you can still get good performance. You can actually do acceleration in storage. I'm going to talk about that later on. And you can actually take emerging algorithms like sequence to graph mapping and accelerate them using near memory engines. And more recently, you can also use non-volatile memory technologies to accelerate different parts of the genomic pipeline and put them together on a single device so that you can minimize the data movement that's happening between different parts. I will not talk about this, but there's a lot of deep learning or machine learning or artificial intelligence that's employed in genome analysis itself, because some of the decisions you need to make are actually sophisticated, and you need to learn these decisions. So we've been also working on architectures to accelerate deep learning that's used in genomic base callers, for example. This is one example over here. We had another micro paper this year that is entitled Swordfish. But there's actually a very interesting interplay between machine learning and genomics as well. And that's going to be even more important in the future, in my opinion. So that was kind of a long, winded introduction to genomics so that I can motivate what's coming next, essentially. But I think the future is actually quite bright in genome sequencing analysis. We just need to revisit how we design our systems and algorithms for it. And this is going to be the theme of my talk, basically. How do we completely rethink our systems, given the situation we're facing today? And on top of that, how do we rethink the applications that we're designing so that we can maximize energy efficiency and performance? So if you're interested, there's a lot more on fast and efficient genome analysis than I can cover in this 5 minutes that I dedicated in this particular talk. And you can find some of our talks online and some of our lectures online. We also have a genomics course. This is not the latest incarnation, but this is one of the incarnations of this course. It's actually being live streamed right now. We live stream all of our courses, so you can find these courses on YouTube. We actually have been holding workshops at both architecture conferences as well as genomics or molecular biology conferences. If you happen to attend them, or you can watch them on YouTube as well. Okay, so that was kind of an example application that's very that dominates our machines today in terms of data movement. And data essentially overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability. And data itself greatly impacts robustness, energy, performance, and cost that we have in our systems. Now, let's take a step back. If we want to design a computing system, you need 3 key components: computation, communication, storage, and memory. And if you look at how we design these systems over 80 years plus or so, essentially we've decoupled these components. Computing unit, communication unit, and especially memory and storage unit, they're decoupled from each other. And the most important, let's say, real estate, if you will, is the computing unit, because it can do computation and nothing else in the system can do computation. So this puts an undue privilege on the computing unit, in my opinion. It essentially makes it much more important than the other units implicitly. And all of the data that's generated by the sensors and stored in the memory and storage unit needs to go through communication units so that it can be processed in the computing unit, and then the computing unit later stores the data into the memory and storage units. So this is a very imbalanced system design, essentially. I'm going to show you some examples of the imbalance, and we're going to talk about how to solve the problem. This is my cartoonish picture of how an existing processor looks like. This is a general purpose processor in this depiction, but the cores can be accelerators also, or FPGAs, or CPUs, or GPUs. They can be heterogeneous, essentially. Essentially, what we have today is cores, but cores are a very small component of the system we design. Everything else, other than the computation units that are in red over here, is dedicated to storing and moving data. We have caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage devices, and other interconnects. Essentially, if you look at a single node today, more than 95% of the real estate is dedicated to storing and moving data. Yet we call these computing systems. Now, you would expect that if you are actually dedicating most of your resources on storing and moving data, you should not be bottlenecked by it. But unfortunately, the system is still bottlenecked by memory and storage today because computation can happen only inside these cores. Now, if you don't like my picture, this is a real chip from AMD, one of the state-of-the-art chips. Similar, state-of-the-art, like 2023 is very similar to 2020. If you look at this green box over here, that's the resources dedicated to L3 and L2 caches. And the rest of the system is not computing. Some of it is memory interconnect, as you can see over here. Some of it is testing, system management, etc. So most of the resources are really dedicated to storing and moving data. And we're adding more. We're actually developing very interesting technologies where we can stack chips on top of other chips. And people like AMD in this particular case is able to stack a cache chip, L3 cache die, on top of a processor die. So we're adding essentially even more caches. And is this the right question? Is this the right thing to do is my question, basically. And I will hopefully answer and show you that while this is very interesting technologically, this is business as usual. And I think it's very important to look at how we should really be designing our systems to overcome the fundamental energy and performance inefficiencies. So we could keep adding caches and caches and many, many layers the way we have done so far, but maybe this is not going to help us significantly in the future. So just so that we're not picking on AMD, this is true across the industry. Basically, this is an IBM chip, for example, and you can see that the green parts over here are circling the L3 and L2 caches, and most of the rest of the chip is still, for example, signaling and interconnects and memory controllers, etc. So most of the chip is essentially dedicated to memory and storage. And if you look at an SoC, like Apple's SoC today, I think of the chip itself, the processing chip itself, as a lot of SRAM, which is true actually. And then there's a lot of DRAM. You can see the relative sizes. And then there's this darkness over here, which is the storage, which normally people think about. And processing happens only inside this chip that has a lot of SRAM and nothing else. Okay, so let me now give you some data based on some of the studies that we have done to demonstrate that data is really a performance energy bottleneck. I'm going to mention energy. I'm going to talk about performance in a little bit. So we've analyzed these workloads that you can see over here, including machine learning inference, video analytics, and browsing. And we found out that more than 60% of the total system energy spent on data movement on mobile devices. And I think this is very significant. This is a modern quantification of the data movement in real systems. And if you're interested, you should take a look at this paper. There's a lot more analysis of the performance, energy breakdowns, etc. And I think this is fascinating. And we were not really exercising the system with the largest applications. These are some reasonably large, but still relatively small applications. So the real numbers are actually larger than 60%. Later, we repeated the study again with Google for machine learning accelerators. This is the Google Edge TPU, if you will, a tensor processing unit. And when we look at large machine learning models like LSTMs or transducers, more than 90% of the total system energy is spent on memory and data movement in these large machine learning models. In some of these machine learning models, more than 99.9% of the energy is spent moving data between memory and the processor. So basically, we have this bottleneck, especially in these large-scale models. So going forward in this talk, I'm going to assume that we want to design architectures that are efficient and intelligent. And in the future, we're going to rely on these architectures. We're trying to design architectures that do decision-making for us, right? These are machine learning architectures. In safety-critical conditions like self-driving, for example, or self-flying, or in space, where the conditions are very adversarial, right? So we really want intelligent architectures. And I think if we really want intelligent architectures, these architectures need to handle data well. So that brings up the question, of course, how do we handle data well? I think there's a 3-step recipe over here. I'm not going to talk about the second one and third one, except I will mention this briefly right now. They're also very important, but this talk is going to focus on especially the first one. Basically, when we design our systems, I think we should ensure data does not overwhelm the components. We need to design a balanced system. This requires us to rethink our algorithms, architectures, and system designs, and co-design of algorithm architecture devices to be much more intelligent. We're going to focus a lot on that. Let me mention the second and third one also. So today, there's a lot of data and metadata that's flowing through the system when we run an application in a processing system. We could take advantage of it so that we could improve the system itself. There are a lot of controllers, caches, memory controllers, storage controllers, etc., prefetchers that exist in especially the memory hierarchy of the system. If we can actually understand and learn from the data and metadata, we can improve the architectural and system level decisions that we're making. Let me give you a very quick example. So we design memory controllers today. Memory controllers normally use heuristics that are designed by humans. And these humans, when they actually design a memory controller, they have limited possibility of thinking because it's a very complex design. And as a result, the policies that are employed by memory controllers are usually heuristic-based. They're not adaptive enough. They don't look long-term into the future, and they don't learn from past actions easily. And as a result, they tend to be very simple. This is exactly the opposite of an intelligent architecture, right? An intelligent architecture would learn from past decisions that it made, and over time, it would improve its policy to be better. So it should not be a heuristic policy, but it should be a machine learning driven policy. We call this data-driven architecture. And I think this is very important. Going into the future, we'll need to have more mechanisms like this in our systems where the system itself makes the decisions as opposed to relying on a human designer who has dictated how it should make the decisions. So I actually spent more time than I expected over here, but this is important. And it's actually synergistic with processing in memory that I'm going to talk about, because this means that every controller in the system, regardless of wherever it is, it's an intelligent agent, and it makes some decisions. It learns from those decisions, and over time, it interacts with the environment so that it can make better decisions. So you can think of these as reinforcement learning agents, just like humans are. Okay, the third part over here is, if you want to handle data well, we should really understand and exploit properties of different data so that we can improve our systems over time again and improve our algorithms and architectures. Data has a lot of characteristics. It has locality characteristics, performance characteristics, it has compressibility characteristics, privacy characteristics, security characteristics, approximability characteristics, fault tolerant characteristics. So there are lots of characteristics essentially. Today, we don't communicate these characteristics. We don't even discover these characteristics at the high level, and we don't communicate these to the hardware architectures or even system architectures. But if you can actually communicate this information to the lower levels of the system stack, we can make much better decisions in our systems. Let me give you another example. I'll pick memory controller as an example. Memory controller today, when it actually makes a scheduling decision, for example, it has two requests from application A and application B. And today, it makes a purely performance-oriented decision that's based on the structural properties of the memory. It basically says, oh, can I service this request faster versus the other request? And it usually picks the request that it can service faster from the memory. But this is not necessarily the right decision. For example, if you know the service requirements of a particular request, you could convey this information, and that other request may be served because of the service requirements. More importantly, potentially, if you know the security or privacy characteristics of a request, and if you communicate it to the memory controller can say, oh, this data that I'm trying to access with this request is security critical. So let me be very careful and not schedule anything else together with this data so that I don't create a side channel that could be exploited by some hacker, for example. So this is another example where a data characteristic aware design can be actually quite important. Okay, I spent more time than expected on this slide, but feel free to, again, stop me with questions. Basically, today's computing systems are very processor-centric. We want to design a much more data-centric system, and I'm going to talk a lot more about that in this talk. Today's computing systems make designer-dictated decisions versus data-driven decisions that make themselves better over time. And today's systems make component-based myopic decisions as opposed to data-aware decisions where the system is aware of the different characteristics of the data. And I think the future needs to be much more data-centric, data-driven, and data-aware, so that we can actually design a fundamentally better architecture and intelligent architecture. These are quite interesting things. Each of them actually can be investigated alone, but they can be investigated together as well. For example, how do you design a processing near memory system that has intelligent controllers that are data-driven and that are data-aware? So these are actually very synergistic with each other. Now, if you really want to actually revisit the system and make it completely intelligent, I believe you need to revisit the entire stack, the way we're designing our devices, architectures, as well as algorithms across the stack. But I believe we can get there step by step, so it's not a humongous task. Over time, I think we can get to this revisiting the entire stack more easily. So I'm going to give you some examples of how we can get there step by step in this talk as well. So if you're interested, this vision is outlined in this particular paper and some of the other papers that we've been writing. Okay, now let me jump into one aspect of this vision, which is how to build data-centric or more memory-centric architectures. If you look at this data-centric architecture, and if you want to actually describe the properties of it, there's a whole world within itself. I'm going to talk about processing data where it resides, where it makes sense. We're going to talk about processing in and near memory and sensor structures. But on top of this, I think we need to rethink how we design memories and communication units such that we are fundamentally lower latency and lower energy. Because data movement and storing data itself, accessing data itself needs to be much more efficient, since data is the most important property that we have. So we need to make it much more lower latency and lower energy. I think this requires us to investigate a lot more into the devices and how we actually organize memory, etc. We need to be much more lower cost in terms of data storage and processing. I think there's a lot of interesting things that could be looked at over here, like compression and fundamentally better algorithms that can operate on compressed data, for example. And also, I think we need intelligent data management. We need intelligent controls handling many different types of things like robustness, security, cost, and performance. I'm going to talk a little bit about this to motivate the first one, but I don't have time to talk about everything over here. But clearly, there's a lot of research going on all of these topics that are quite exciting. Now, let's jump into the first point over here. I call this processing data where it makes sense. Today, we have no option. We have to move the data to a computing unit, which is a CPU, GPU, FPGA, machine learning accelerator, pick your favorite. And even within this computing unit, we have to move the data from buffers to computing elements. So we have very limited options. Processing data where it makes sense means that increase your options. Basically, enable processing capability everywhere possible. It could be the SRAM on the chip. It could be the DRAM outside the processing chip. It could be the storage. It could be the sensors. It could be the network interface controller, essentially everywhere. And then we need to figure out how to partition the computation such that it happens at the most interesting place. If it not interesting, but most in the place that is the best fit for that computation to maximize some metric like performance or energy efficiency. If it's the processor's computing unit, so be it. If it's the DRAM, so be it. If it's the storage, so be it. If it's the sensors, so be it. So this opens up a whole new world of distributed systems, essentially, and the entire system becomes distributed, and we have to actually distribute computation to it. Now, this is not a new idea, especially processing near memory is not a new idea. These are some earliest papers that I could find on the topic. And if you actually happen to know some earlier papers, please let me know. People have called it logic in memory in the past. We're going to call it processing in memory, not that different. And this is another paper that I would encourage people to read. So people have looked at this for a long time, as you can see. So why is it interesting today? Why hasn't it happened? And why should we expect it to happen? Basically, I should say that it's already happening today. We're already moving towards near memory computation. And I think this is going to be even more important. And let me give you why we're moving toward in-memory computation. Basically, we're stuck with nowhere else, essentially. We're having problems with memory technology. Memory technology scaling is not going well. I'm going to talk very briefly about this. There are issues like RowHammer that create fundamental robustness issues, including reliability issues, security issues, availability issues. And many of these technology scaling issues demand intelligence in memory. So we cannot easily increase memory performance anymore. As a result, we need to figure out how to use existing memories with lower, not so fast increasing performance so that they can scale better. And on the application and system side, we have a huge data access bottleneck. Energy and power are key bottlenecks, and data movement energy dominates computation energy. I'm going to give you some examples of this. And at the same time, human beings have changed. We need actually performance. At some point, we were very much performance focused, but right now, energy is a key issue, and increasingly, sustainability is a key issue. So we want actually performance, energy, and sustainability all at the same time. We don't want to say performance at all costs, because energy is key. So today, we want to actually get higher performance at lower energy and better sustainability. And I believe we can actually achieve this by minimizing data movement. So basically, our designs are squeezed in the middle by memory technology and applications as systems, and they're pushing us to do something different with our systems today. Okay, now before I go into a little bit more, let me give you the processing in memory landscape a little bit. Essentially, people are examining interesting solutions like 3D stacked memory, where you have a logic layer underneath memory layers. And you can actually put some computation in the logic layer near memory. I'm going to talk about this when we have time. People have been developing some prototypes that can do processing inside DRAM. This is one example. And more recently, the UpMem company has put general purpose processors inside the DRAM chip. I'm going to talk about this hopefully toward the end of this talk. So you can actually do general purpose computation inside the DRAM chip today. And even more recently, major memory manufacturers have been putting processing capability, especially matrix multiplication type of capability, to accelerate machine learning applications inside the DRAM chips. That includes SK Hynix as well. And Samsung, for example, has also put a buffer chip together with Meta so that they can do recommendation inference in this buffer chip that is essentially reconfigurable. And Alibaba has also developed their own DRAM chips to do recommendation inference. So these are actually modifying the memory system so that you can do near memory processing, as we will discuss. And there are many other experimental chips and startups that are doing many, many other things, even more fancy things that we will briefly discuss. And there's more, actually. It doesn't fit in one slide. This is more recently published at the Computer Architecture Letters from SK Hynix with a CXL type of interface. People have been actually rethinking the memory interfaces, even in industry, so that you could actually enable memory to expand better, despite so that you're not limited by the pins in a processor. And also, this sort of interface enables offloading of applications to the memory side. So this is already happening in industry. So this is good news. If I was actually giving this talk last year, you wouldn't see this picture on my slides. But this has happened this year. And more also similarly, other manufacturers are also exploiting the CXL type of interconnect so that they can actually offload computation over the interconnect to near memory processors. We're going to talk more about this toward the end of this talk. So in real life, things are happening. So, okay, let's talk about why they're happening. By the way, feel free to stop me if there are questions, Ramzi, or anyone else who could stop me. I'd be happy to take questions.
We're going to take 2 questions and continue.
Sure.
So the first question is from Marwan. He's saying, does the embrace of memory-centric computing signal a departure from the traditional von Neumann architecture, implying a fundamental shift in established computing design principles?
Mm-hmm. Yeah, so that's a great question. Basically, so in the aggressive incarnation of in-memory computing, near-memory computing, yes, absolutely. So we would like to move from, let's say, von Neumann type architectures so that we can actually look at a more, in my opinion, brain-inspired type of architectures where memory and computation are not decoupled. In von Neumann architecture, memory and computation are decoupled. But having said that, I should also say that von Neumann architecture makes sense in many cases. It's very easy to reason about. I think we really need to enable in-memory and near-memory processing such that it could also coexist with the von Neumann principles. And I'm going to talk about that also. So that's a very good question. So that's why the answer is both yes and no at the same time. But I think we'd like to examine both.
Okay, this is a comment from Wael. He's saying, never thought that this would be possible one day. What a great time to be alive.
Yeah, I like that comment. I agree with you. Yeah, yeah. So it's a great time to actually...
Okay, go ahead.
Yeah, so it's a great time to be doing research in this area also, because you could actually have almost immediate impact on how the computing systems are, let's say, rethought in a fundamental way. Okay, so thank you. Yeah, feel free to, again, stop me if there are questions coming up. So I was actually motivating why things are happening. So let me give you the device level, circuit level motivation a little bit. And then we're going to talk about the application level motivation. And then we're going to see some example memory-centric architectures. So we've been working on memory systems reliability, dependability, etc. for a long time. This is a paper that we presented at the International Memory Workshop, which is an industry-heavy workshop. You can take a look at it. Here, we argued basically we need to rethink the memory from a systems perspective and redesign the systems for better scaling of memory. And one of the reasons, this is not the only reason, but one of the reasons is memory technology scaling is not going well. Basically, as you reduce the size of a memory cell, DRAM cell or flash cell, but we're going to focus on DRAM in this particular lecture, it becomes less reliable. And this reliability issue causes problems. Essentially, you may have data corruption, for example. This data corruption can be exploited by hackers to actually take over the system. And this is an example problem. This basically, we found out through our research that one can predictably induce errors in most DRAM memory chips by hammering a row. This is called the RowHammer problem. Some people may be familiar with it. Essentially, if you look at memory, memory consists of rows of cells. It's a two-dimensional array of cells. And if you happen to hammer one row, meaning activate and then close it, or open and close it, apply high voltage and low voltage to it repeatedly, it turns out because the cells are too close to each other, and there's a lot of electrical interference between the cells that you're activating and the word line you're activating and the word lines in the other rows and the cells, some cells that are vulnerable in physically adjacent rows get corrupt. We call this a hammered row. We call this a victim rows. Clearly, this should not be happening because this is not out of the specification of memory. But because of the technology scaling issues, this happens today, and this is called the RowHammer problem. And this happens in essentially all the chips of all major manufacturers today. There are 3 major DRAM manufacturers today. And at the time we tested, it was more than 80%. But today, 100% of the chips are vulnerable at the device level. So this is a simple hardware failure mechanism that also creates a widespread system security vulnerability, because people have shown that if you actually figure out how to flip a bit using RowHammer, you could take over a system, become root essentially on Linux. I'm not going to go into the details of this. Essentially, you're breaking memory isolation, and you could actually design an attack program that would get permissions, escalate privilege in a system that otherwise, where otherwise it has user level privilege, or it can leak private data. So that's why this is actually very interesting, and people have been doing a lot of research on hardware security side on RowHammer, and people have been trying to solve the problem, but the solution is not easy. So if you're interested in this, this is the original RowHammer paper. You can take a look at it. I also give RowHammer talks, but this time we decided to talk about memory-centric computing. But it's just an example where the memory technology scaling issues are real, and there are other papers that we've written. If you're interested, you can actually find tutorials and talks as well. So why am I telling you this? So this sort of scaling issues are very difficult to solve at the device level unless you're willing to pay a lot of cost. So people have been developing intelligent controllers to fix the problem. Intelligent controller, for example, can figure out which rows are being hammered by counting which rows are, how many times each row is being hammered, and then refresh adjacent rows. This is one of the solutions that we have proposed, and one of the solutions that is being implemented in industry today. So basically, this problem caused industry to implement memory controllers inside the DRAM chips that are much more intelligent. You can find this information in ISSCC, which is a major circuits conference this year, from SK Hynix. And essentially, they finally acknowledge the problem and they develop solutions. Essentially, they have a simple memory controller inside the DRAM chip that occupies some area that is intelligent, meaning it counts, accesses the different rows, and it takes some action based on that row tracking. They don't describe exactly how this works, but you can potentially figure this out by some reverse engineering if you have your hands on this chip. So this is good news, I would say, because industry is actually trying to solve these critical problems that are important for reliability, security, robustness. But also they're putting intelligence into the memory chips themselves, which means that this sort of intelligence can be combined with other levels of intelligence. You can do other processing inside this controller that's already being put into the DRAM chips. That's why this technology scaling is important, I think. And it's not just one company that does this. There are other companies, like major companies like Samsung, that are also putting intelligent controllers inside their DRAM chips to solve this sort of technology scaling issues. And I think we will see more and more of this, because as technology scales, meaning as we want to put more memory cells in a given millimeter square so that we can actually deal with the huge capacity increases that we need in terms of memory, we're going to see more and more problems. I will not spend more time on this, but basically, it's very difficult to solve these problems at the device level. We have more recently shown at the ISCA conference in June that there's another redisturbance phenomenon called row press that makes RowHammer even worse. And I will let you take a look at it because we don't have a lot of time. And if you're interested, this is one of the most recent lectures that I delivered on RowHammer that could be found on the Stanford YouTube. This talks about the current status and what we think will happen into the future and how things are going. It also includes a discussion on row press. So basically, I think the solution to this sort of issues is going to be intelligent memory controllers, which is in line with near memory processing, essentially. You may say that, okay, maybe if the technology is not scaling very well, we should look at other emerging memory technologies. And I absolutely agree. We should be investigating emerging memory technologies, and there are many different types over here, like ferroelectric RAM, phase change memory, STT-MRAM, other types of magnetic memory, etc. I think we should be investigating them. Unfortunately, all of these memories have some issues. This is one paper that we wrote some number of years ago, where we showed that this technology, phase change memory at the time, has a lot of issues. So you actually need to build an intelligent controller around it so that you can actually solve some of those issues. So essentially, we have nowhere to escape. As we want to store more data in large-scale memories and storage, these memories and storage will not be easily reliable. So we need to design intelligent controllers that could fix some of these issues so that we can enable better scaling and avoid failures. Okay, so that was the device level perspective, or circuit level perspective, very low level perspective. Now let's take a look at the very high level. If you look at the high level, basically we have a data access. That's the major bottleneck today. I'm going to motivate this even more. Energy consumption is a key limiter, and data moment energy dominates computation energy. I'm going to talk about these very briefly, but before I move on, I should give you a pictorial motivation. Essentially, do we want a future where the world is nice like this, or do we want a future where we cannot live in the world? I would pick the first one, but I would also want the productivity of the second one. Basically, we want high performance, energy efficiency, and sustainability all at the same time going into the future. Now, unfortunately, we're violating, essentially, our design principles today violate everything that goes for this goal, high performance, energy efficiency, sustainability. We're moving data all over the place. Data access is a major performance and energy bottleneck today. We need to move the data from wherever it's generated, wherever it's stored, to particular processing units that are far away. As a result, we're causing great energy waste. And we're also causing performance loss because moving the data is not cheap in terms of latency and bandwidth. And we try very hard to overcome that performance loss. We make our systems extremely complex, both software and hardware. We add massive levels of multi-threading, for example, in GPUs. We add many, many levels of cache hierarchy for all of our systems, essentially, buffering hierarchy. And this complicates things. We add prefetching. We add heavy levels of out-of-order execution, for example, in some of our systems that we design, either at the software level or the hardware level. So essentially, we go to great lengths to overcome the performance loss of data movement. In the end, sometimes we overcome some of it. Most of the time, we don't overcome most of it. And in some really bad cases, none of what we do helps performance. But all of these things that we're adding to the system actually compound the energy waste because they add more components. They add even more data movement into the system. As a result, we're in this vicious cycle right now. Data movement causes great energy waste. To overcome the performance loss, we cause even more great energy waste in our systems. So I think we need to break this vicious cycle. And I think breaking the vicious cycle really requires us to pinpointing the problem. And I think the problem is actually very simple. We're processing data far away from the data. Why not enable processing near the data, essentially? And essentially, basically, today's processors are processing data at great system cost. Now, let me give you some quick data. This is a very well-known problem. But unfortunately, even though it's a well-known problem, I think we should really move the needle in a big way forward. This is a one-page article from Dick Seitz. Dick Seitz was the chief architect of Alpha processors. Their team designed some of the most sophisticated, fastest processors of its time in the 1990s. And after they designed one particular processor, he wrote this one-page article, which is entitled, "It's the Memory Stupid." Basically, it's all about the memory. He basically says that my team designed this fastest processor of its time. It's capable of completing 4 instructions per cycle, per clock cycle. Unfortunately, on this really important workload, it's able to finish only a very small fraction of that, basically 5% of that. So it's basically 1 instruction every 4.7 cycles or so. So essentially, we're wasting a lot of the processing capability of the processor itself. And why? Basically, he says that on this important workload, the processor needs to wait for data from memory significantly. Essentially, this is the memory bottleneck. And he finishes this article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I agree with this, but I would also say that we need to rethink the entire system to overcome this sort of bottleneck. Okay, so I spent some time over here, but I would encourage people to read this sort of articles. It's very instructive, in my opinion. This is my data from my own PhD thesis. We worked together with Intel to analyze the applications that we're designing to build their microprocessors, state-of-the-art microprocessors at the time. And we found out that most of the time, the processor is waiting for data on these memory-intensive applications, as you can see over here. And we proposed some solutions to it, which you can read about if you're interested. So that was 2003 or so. Now, fast forward to 2015. This is data from Google. Google wrote this beautiful paper at ISCA 2015, where they showed on a state-of-the-art Intel processor that they employ in their data centers, on all of the data center workloads that they have in their system, according to them, most of the time the processor is waiting for data. It's doing useful work only a very small 10 to 20% of the time. So this is happening because the processors are not designed to deal with this data, essentially. So basically, we're wasting huge amounts of performance in our systems today. Okay, so what about energy? This is a slide that I borrowed from Bill Dahl. You could argue with all of these numbers over here, but the trend remains the same. A 64-bit double precision floating point operation is very cheap today because of technology scaling, logic scaling. The energy of a particular logic operation on a logic process is very cheap, 20 picojoules in this particular case. You could argue with these numbers, as I said. But a DRAM read or write access is 16 nanojoules. That's 800x difference. So essentially, today, a memory access consumes between 1 to 2 orders of magnitude the energy of a complex addition. Then the question is, does it really make sense to bring data from using multiple memory accesses to the processor chip and then write back the result to the DRAM chip or memory chip again? This is consuming 3 times 800x to their very simple, energy-simple operation. And in order to overcome the energy disparity between computation and memory access, you need to have very high amounts of locality in your caches in the processor chip. You need to be able to reuse that data many, many times, thousands of times actually in many cases. So unfortunately, we don't have that much locality in our programs, even if we try to get that locality in many cases, of course. In some cases, you do have that much locality. But in many applications like graph processing, for example, you don't have much locality. Okay, so that was kind of the bright picture. The picture is actually even worse. If you look at simple arithmetic, like a 32-bit addition. Today, neural networks are neural network inference. People are trying to actually go to binary neural networks, 1-bit arithmetic, 4-bit arithmetic, 8-bit arithmetic. Let's take a look at 32-bit add. A 32-bit add is much less energy than a DRAM access. Basically, there's a 6,400 times disparity between a DRAM access and a 32-bit addition. And if you actually look at the storage, disparity between storage and addition, that becomes actually even larger. I don't want to put that number over here because that's between 1 to 2 orders of magnitude worse than main memory. So basically, we're wasting a lot of energy today by moving data from the memory and the storage to the processor, such that the processor can complete a very simple, from an energy perspective, operation. As a result, we see this picture in the end-to-end applications. More than 60% of the system energy is spent on data movement on these applications on the mobile devices that I showed you. And more than 90% of the total system energy is spent on memory in large machine learning models. In many cases, more than 99%. So I'm going to get back to these works. So I will argue that basically we do not want to move data. We want to enable a paradigm shift where we can do computation with minimal data movement in every place possible. We want to compute where it makes sense, where the data resides or where it's generated. We want to enable the computation capability in all of those places. And I think this is, in the end, making computing architectures more data-centric. Now, in this talk, I'm not going to talk about everywhere, but I truly believe that processing really needs to be happening everywhere. And in the longer term, hopefully, we will move to a place where processor core or computing unit, there's no CPU, basically. There's no central processing unit, essentially. Everything is a distributed agent that can do computation on the data. And data and computation are kind of merged, maybe similar to our brain. I don't claim to know how our brain works, but it definitely doesn't work with a central processing unit as much as we think it does. Essentially, every place in the computing system is a distributed agent that can do intelligent actions on the data that is near to it. So I'm not going to go through that. I think this is kind of the very interesting perspective from a distributed systems perspective. We're going to still have the CPU today. We're going to offload computation to the memory and storage devices. Essentially, we're going to store interesting applications on memory and storage as it's done today. And we're going to offload computation. Processor will be able to query memory and storage, say, ask memory, can you execute this function for me? And the memory will execute that function and return the results. So this is an accelerator model. CPU is still central, if you will. It still coordinates the application execution. It's much more easily adaptable in the von Neumann paradigm and in the way we're designing our systems. But it adds this processing near or in-memory capability in the memory and storage. But still, even this accelerator model brings about many, many questions. How do you design the compute-capable memory and the controllers? How do you design the processor and communication units? How do you design the communication interfaces in the software and hardware? Today, the CXL interface, for example, Compute Express Link interface, enables more flexibility such that the processor actually can offload computation to some other device. It could be a near memory device, for example. So today we're living in a good world where the interfaces are becoming more flexible. So that's good. But we still need to make them even better in the software and hardware side. How do you design the system software compilers and languages? And how do you actually program these things? How do we redesign the algorithms? And how do we rethink the theoretical foundations of computing? So this is very exciting because there are many, many questions across the stack, as you can see over here, all the way from how do we design the devices to do computation together with the memory, to algorithms that can fit those devices and everything in between. And I will also mention over here that we need to rethink the theory of computation as well. So far, theory of computation has assumed a compute-centric model, processor-centric model, von Neumann model, essentially. I don't want to necessarily call it von Neumann, but it's actually a processor-centric model, which assumes that everything moves to the processor. But if the data is the most important thing that we're dealing with today, the analysis methods that we've developed for our algorithms will not work well. Because if you look at, for example, analysis of algorithms, people usually analyze the complexity of algorithms using the big O notation, for example, or big theta notation, which essentially counts operations. But maybe that's not the most important thing in a data-centric system. In a data-centric system, you're bottlenecked by data, how much you can move the data. So how much data movement you have should be a first-class citizen in terms of how we actually evaluate our algorithms. And there's a new class of algorithms that I believe we need to develop to take advantage of the underlying memory and storage structures and the computation that happens in those structures. I'm going to especially talk about this a little bit in the processing using memory systems. Okay, so I'm going to, after this point, I'm going to talk a little bit about what we are going to do in processing in memory. But I will not have time to cover everything. This is an archive paper and a book chapter we have written on this topic. If people are interested, this is a great place to get initiated on this topic. We're going to update this book chapter periodically. It's kind of overdue, but you can find a lot more information. We also have a processing in memory course. It's not the latest incarnation. You can follow this course on YouTube. You can also, if you decide to hold it again, you're going to find it live streamed. And there's some other incarnations. We also have an SSD course and genomics course. And we've been holding real processing in memory tutorials in major conferences. And you can find all of these on YouTube openly if you're interested. Oh, I think I skipped some of these, but it's fine. You can find all of this information. I'll be happy to share these slides. If there are any questions, I can take some right now. Otherwise, I'm going to go into a little bit more depth right now.
Okay, so there are actually some questions that we're going to take.
Okay.
The first question is from me. To what extent does memory-centric computing aim to challenge the conventional assumption that general-purpose computing inherently translates to lower performance and higher energy consumption?
Yeah, I mean, that's a good question. Basically, in my opinion, the sky is the limit here. I don't know how. I mean, it challenges it completely. Basically, as I mentioned, this distributed agent-based processing system is a completely different way of designing systems today. I'm going to show you another completely different way of designing systems with processing using memory in a little bit. So I believe we don't know the limits of this at this point. We really need to design new computation models. And in some cases, you can reduce energy by 60 to 100x, for example. But I cannot tell you that it's going to be the limit. Maybe someone will come up with a device that can do a very efficient analog computation near memory. That's going to make it 1000x more efficient. I don't know. That's a great question, though.
Okay. So the next question is from Hisham. He's saying, how do we machine learning on embedded systems, TinyML, can contribute to all the key objectives you listed?
Yeah. So that's also a great question. I'm going to mention some work on machine learning that tries to accelerate machine learning, like TinyML type of models on edge devices, using processing near memory. So, and also, if you actually are more aggressive in your algorithms, you can do bitwise machine learning even more efficiently. So I think this sort of edge machine learning systems like algorithms and systems like TinyML, they're a good fit for processing near and inside memory. So hold on to that. I'm going to mention that in a little bit.
Okay, so you can go ahead.
Okay, wonderful. Keep the questions coming. And we still have 1 more hour, correct? Okay, I'm going to assume that we have 1 more hour, so I'll keep going. Okay, so now we're going to go into a little bit more detail. But before I go into more detail, I should define some terminology. This is an area where terminology is not very nicely set, if you will, and we're trying to set the terminology. early people who did processing in memory called it logic in memory, which is not a bad term actually. We'll call it processing in memory, which is actually a commonly used term. But processing in memory is a general term, in my opinion. It encompasses everything that you can do in or near memory. I believe there are two fundamental approaches to processing in memory. Let me demonstrate this. Hopefully you can see my hand over here. There I have two hands. Basically, this hand over here is the processor. This hand over here is the memory. I'm going to talk about what processing near memory is. Today, processor and memory are far away from each other. Right? Processing near memory is that means that we're going to put the processor closer and closer and closer and closer and closer to memory, such that at some point it's integrated together with the memory, different memory structures inside the DRAM chip, for example, or it could be in a logic layer, it could be in a memory controller. But the processor, meaning logic itself, is distinct from the memory itself. So these are designed separately. Okay. So in that sense, it's very similar to the way we design our computers today, except we're putting the processing units closer and closer. The processing unit can be anything again. It could be a CPU, GPU, accelerator, it could be a functional unit, etc. So this is what we know today, except we're going to push it inside the DRAM chip, for example, or the memory chip. And this is going to be easier to program as a result, because we can actually preserve the programming model of accelerators today. And this is also going to be less disruptive. As a result, this is being adopted by industry today. All of those pictures that I showed you earlier are processing near memory designs, where there's a distinct logic and distinct memory, and they're put together in some way. Now, processing using memory, let's go back to this picture of today. This is the processor, this is the memory. Processing using memory is fundamentally different. You remove the processor, forget about the processor, forget about logic as something being separate from memory. Now, let's take a look at this memory. This memory is very interesting because, yes, it has memory function, it can store data. But if you look at the analog operational properties of how this device is designed, those analog operational properties enable this device to also do computation. Essentially, rethink the memory device such that it can also do computation using analog functionality. That's why we call processing using memory. And this is fundamentally different because you don't design a logic unit to do the computation separately from memory. Memory itself can perform the logic computation, essentially. I'm going to give you examples from DRAM for this, but in my opinion, any memory is actually capable of doing this sort of processing using memory computation. Actually, I'll give you some examples on flash and emerging memory technologies like RRAM as well. Now, this is very interesting because this opens up a fundamentally different model of execution, as we will talk about. In the end, processing using memory, in my opinion, is actually a lot more efficient than processing near memory. However, it may be limited in what kind of operations it can do. In the end, I believe these two paradigms, processing using memory and processing near memory, need to be combined together so that we can actually design a much more efficient system going into the future. And hopefully there will be works that look at combining these paradigms together in different ways. So it's a big world out there where you can actually have a lot of impact with a lot of interesting research. Now, let me expand on this taxonomy. I just talked about the nature of computation. Using means you use operational properties of memory structures to do analog computation. Near means you add logic close to memory structures. But then there's also the technology aspect. You can have different technologies where you can actually do processing, right? I give you some examples over here. And then there's the location aspect. Location may incorporate one or more technologies, but locations actually can be different also, as you can see. In the end, I believe we need to enable computation everywhere in every technology, which is the really interesting research problem. In the end, if you want to classify a processing in memory type, I believe you need to talk about this tuple of nature, technology, and location. And one can combine multiple processing in memory types in a system as well. Of course, once you actually start combining multiple different types of these things, programming will be an issue. And I think we need to develop programming models to take advantage of this heterogeneous computing devices that exist all over the system. I'm going to talk about that. But we're going to start simple. We're going to basically think about memory as an accelerator. So you have this memory, and you have some compute capability inside the memory, either using or near memory. And we're going to treat this as an accelerator. We have many, many accelerators today. We're designing our systems. Why don't we have another accelerator on the memory side that has high bandwidth and low latency access to huge memory structures? That's not bottlenecked by this memory bus. Okay, I'm going to talk about processing using memory first, and specifically processing using DRAM. Here, the nature is using, technology is DRAM, location is main memory. I'm going to give you some example of works that we've been doing. Just to summarize, essentially, this is fascinating. Even with a technology like DRAM, we can support bulk bitwise and or not and majority operations. We can do copying and initialization in memory very efficiently. We can do true random number generation, physical unclonable functions, some security infrastructure essentially. And if you want to do more complex computations, you can use DRAM as a lookup table such that you can look up values of a computation. I'm going to give you some examples. And you can do a lot of these at low cost with a small amount of changes to the DRAM circuitry. Essentially, we're using analog computation capability of DRAM. One of the key principles that we're going to use is to activate multiple rows. If you activate multiple rows concurrently, this performs computation. And essentially, this computation is very efficient. We're going to see significant performance energy improvements. And these are some papers that I will refer you to. I'm going to talk about the RowClone paper first and then the Ambit paper next. But hopefully it'll be interesting. And as I said, this sort of operation is generalizable to any memory technology. I'm going to give you some examples from other memory technologies also. But let's start simple first. As I said, you can actually rethink the entire system and redesign the devices completely. But let's think about what is the minimal thing that we can do to get good benefits. This is kind of getting there step by step that I mentioned earlier. How can we actually enable this paradigm shift step by step with simple changes? I'm going to talk about data copy and initialization to begin with, which is an important function that exists in systems today. Essentially, you need to copy data or initialize data for forking processes, for example, for security functions, checkpointing, cloning virtual machines, doing page migrations, and there are many, many other cases, basically. And in fact, Google, in that paper that I mentioned earlier, they basically show that in their data center workloads, about 5% of the execution cycles of averaged across all of their workloads is occupied by these two functions only, memmove and memcopy. This is fascinating. Basically, they're doing copying, and that's occupying 5% of the all cycles across many, many functions, only two functions. Okay, so how do we do copy today? Basically, if you want to copy the source page, the white page over here, to the gray page, you need to go through the processor. Basically, we have a processor-centric system. Memory cannot do operations on its own. The processor needs to do loads and stores to load the page byte by byte all the way into the L1 and store it to the destination page byte by byte all the way into the memory. Now, clearly, this is high overhead, right? We want to do in-memory processing, meaning we want the CPU to tell memory, please copy this page to this other page in memory and don't bother anything else into the system. That's what we want to enable, basically, this sort of copying inside the memory without going through the processor. Now, this is low latency because we're going to exploit the internal parallelism in memory. This is low bandwidth utilization on perhaps the most important resource, which is the memory bus that we have today, and low energy as a result, and no cache pollution in the caches, and no unwanted data movement, which is actually good for, again, energy as well as performance, because this memory bus can be utilized by someone else during that time that actually really needs the memory bus as opposed to wasting the memory bus for this copy. I'm going to show you a mechanism. Today, for example, this 4 kilobyte page copy, which is a small page copy, relatively small copy, takes about 1,000 nanoseconds and 3.6 microjoules. I'm going to show you a mechanism inside the DRAM that reduces that significantly to 90 nanoseconds and 0.04 microjoules in an unoptimized fashion. So if you optimize it, you can actually get even higher benefits. And the idea is very simple. So we're going to look at this DRAM subarray again that I showed you earlier in RowHammer. Basically, you have this two-dimensional array of cells, and you have a row buffer. And if you want to copy a source row to a destination row, we're first going to activate the source row, which brings the data into the row buffer. These are sense amplifiers inside the DRAM. That's the first step. In the next step, we're going to activate the destination row, which will disconnect the source row from the sense amplifiers and connect the sense amplifiers or the row buffer to the destination row. Basically, this will copy the data that we copied into the row buffer from source row into the destination row. Basically, by doing two consecutive activates, we will use this row buffer or sense amplifiers as an intermediate buffer in memory to copy from one row to another, and with negligible hardware cost. So this is actually a very simple idea, and it gets you significant performance improvements, latency reductions in a 4 kilobyte page copy, as you can see, more than 10x. And the energy reduction is even larger because you're not moving data across these huge interconnects, right? 74x over here. And ignore these other bars over here. These are basically, depends on where the data is. If they're not in the same subarray, you need to move the data a little bit more. But we actually have solutions to that is not depicted in this particular case. I'm going to actually mention that briefly. So this is the idea of RowClone. It's essentially very simple. It's using the DRAM substrate to do data movement. This is why it's processing using DRAM. So it turns out, to be able to do this completely reliably, you need to modify the DRAM chips by little. I'm not going to tell you exactly how. You need to read the paper, but very little hardware cost. It turns out you could actually do this on off-the-shelf DRAM chips. If you actually buy a DRAM chip, if you have a memory controller that you can configure, this paper showed that using an infrastructure that we developed called softMC, they could violate the DRAM timing parameters. And if you violate the DRAM timing parameters such that you could do back-to-back activates very quickly, you could get row copy operation inside the DRAM chips. I think this is fascinating. And you could actually use this for initialization also, because initialization is a special case of copy. You basically initialize one row to all zeros and then copy it to other rows. So basically, the takeaway is you can actually do this on real DRAM chips. So we built off this work, and we showed that you could actually do this. We built a prototype that is open source right now, which we call PyDRAM. Essentially, we have this FPGA-based prototype that enables you to automatically violate DRAM timing parameters and offload row copy and row initialization and also random number generation functions inside the DRAM chip. This is how it looks like. Essentially, we have this RISC-V processor that runs the programs. And when it gets a row copy request, page copy request, or page initialization request, it offloads it to a memory controller. And this memory controller violates the timing parameters to do the page copy inside the DRAM processing using DRAM in off-the-shelf DRAM chips. I think this is fascinating that you can do it in off-the-shelf DRAM chips. And if you're interested playing with it, you just need to download our code and find your own FPGA, etc. And we'd be happy to support it if you're interested. And you can actually generate results like this on a real system with a relatively not so powerful core. The benefits of actually doing initialization and copy inside the DRAM chip processing using DRAM, using RowClone is actually significant, much more significant than what we reported with a powerful core. Okay, so that's the PyDRAM infrastructure. And this is just one example of what you can do in terms of data movement, reducing data movement, doing copy and initialization inside DRAM. And there's a lot more. If you want to learn more about that, you can take a look at this lecture and some papers. So this was copy and initialization. Can we do more? Essentially, we've also discovered that you could do more in DRAM. You could actually do bitwise AND or NOT and majority function. I've already said this, so I'm going to give you some examples. I believe new memory technologies enable even more opportunities because fundamentally DRAM, whenever you read a row, it destroys the row. So you need to fundamentally move the data, copy the data somewhere. So RowClone is really useful to do computation also. But some emerging memory technologies are non-volatile, meaning that whenever you do a read, you don't destroy the data. And as a result, these are actually even more capable of reducing the data movement. And they also can operate, they can also do analog matrix vector multiplication, as we will briefly discuss. But unfortunately, these emerging memory technologies are not there yet. There's still time for them to emerge, if you will, at a large scale. At some point, hopefully, they will emerge and they will coexist with DRAM in the system. Now, let me tell you how we can do in DRAM bitwise operations. So I'm going to show you 3 rows over here across many rows in a subarray. And we're going to activate these 3 rows concurrently. And these 3 rows are connected to a single bit line. And this is the sense amplifiers, a cross-couple inverter, essentially. Each row actually has 8 kilobytes of data. I'm going to show you only 1 bit cell. And imagine that whenever you concurrently activate these 3 rows, you're actually activating 8 kilobytes. So you can actually do the operation that I described over here on 8 kilobytes at a time. If you actually activate many, many subarrays in DRAM, of which there are thousands, you could actually do this bitwise operation on 8 million or 10 million or even more bits in a given DRAM chip. Of course, you will need to supply power to the DRAM chip and also make sure the heat comes out of the DRAM chip because you're doing computation inside the DRAM chip right now. But assuming you actually do all of these, you should be able to do massively parallel bitwise computation at DRAM chip. So how does it work? We're going to activate these 3 rows concurrently. This is called triple row activation. Once you activate these 3 rows concurrently, the capacitors over here that store the charge will be connected to the same bit line. And based on fundamental circuit principles, if at least 2 of these capacitors, 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So basically, final state can be expressed as this Boolean function, which is essentially a bitwise majority function. So what we've done is essentially a bitwise majority computation across these 3 rows. It's fascinating. I think bitwise majority is very interesting because you could actually redesign your algorithm such that it does a lot of bitwise majority operations. Donald Knuth, in his The Art of Computer Programming book, actually talks about this. If you're interested, you can take a look at it. Now, it's interesting. It's even more interesting if you actually set C to 1 or 0. If you set C to 1, you get the OR of A and B by rewriting this equation. That's what you get. If you set C to 0, you get the end of A and B. Now you have bitwise AND and bitwise OR. This is fascinating. Now, this is not enough because this is not functionally complete. What does that mean? Basically, we don't have a NAND or NOR, or we don't have a NOT essentially. So in this particular paper, in the AMBIT paper, we say that doing NOT, an inversion of a row, requires a little bit more circuitry overhead. In addition to being able to do triple row activation, to do AND and OR, you should be able to take the value that's stored on the other end of the sense amplifier. So you actually have the bitwise complement function, right? If you actually activate one row, you read the data from this side of the sense amplifier, but the other side of the sense amplifier actually has the complement of the data because of the way this cross-coupled inverter operates. So you actually already have the inversion function. You just need to feed it to the same subarray or some other subarray, and this requires some more circuitry changes. So you can actually implement NOT as well. As a result, you're functionally complete. This means that you have a Bach bitwise functionally complete system. You should be able to theoretically take any application and rethink your algorithms such that it can execute using this Bach bitwise manner. And I think the jury is still out to change many algorithms to it. Because it's functionally complete, I think this can be done. But I think when we actually first looked at the paper, we to first develop these ideas, we said there are some algorithms that are very good fits. For example, people already use a lot of Bach bitwise operations in databases. They do bitmap indices and huge amounts of data, actually, huge bit vectors, for example. Some people actually rewrote the databases such that they can operate on huge amounts of bitwise operations. Some people at Microsoft, for example, rewrote their web search engines to do the same thing. And there are many, many other algorithms over here that are already written with Bach bitwise operations. So we ported one of the databases, Bitweaving database, to our simulator that can do this sort of Bach bitwise computation inside DRAM. And we see significant performance energy improvements, as you can see over here, end-to-end, 4 to 12x. And I believe the improvements can be even greater if we really rethink the algorithms to match the hardware and also make the hardware even more flexible. There are some flexibility issues that we will talk about. And I think there's even more that can make this sort of computation even more efficient. So this is promising, as you can see. And if you want to read more, you can take a look at this AMBIT paper that we published in 2017. And if you are interested, we actually have a book chapter that talks about some of the challenges and some of the issues that I think need to be solved, including future work. Now, how can you take advantage of this easily in a von Neumann system, in a way that is easily programmable by a programmer today? That's the framework that we wanted to develop next, and this is the SimDRAM framework. I will very briefly mention this. Essentially, you can implement any operation using this sort of framework using memory. Essentially, for example, the programmer can specify a matrix vector multiplication. They just need to specify it as a circuit that looks like this, and or not logic. It could be a convolution, it could be multiplication, it could be a division, it could be a logarithmic operation, it could be anything essentially, many machine learning operations potentially. We automatically generate a majority inverter graph out of this using design automation tools. And then to minimize the amount of computation. And then and also data moment. And then we convert this to a microprogram. So this microprogram is essentially a sequence of DRAM commands, triple row activation, row clone, etc. And this microprogram is stored with this new operation. So for example, if you want to do a convolution, this microprogram, there's a corresponding microprogram, Bach bitwise operation convolution, that's stored in memory. And when the user needs to modify their applications using either compilers or handwritten code to include these operations. And once that operation is included in the program, it gets shipped to the memory controller during execution. And the memory controller fetches the microprogram and executes this microprogram to execute this particular operation. So I think this is actually fascinating and nice because it makes the programming easier from a programmer perspective. The programmer needs to think about instructions only. And these instructions have microprograms associated in the memory side that will be executed on the memory side. And we showed in this particular paper, you can actually implement 16 complex operations. And on 7 commonly used real-world applications, you get significant throughput improvements over a CPU and high-end GPU. And you get significant energy efficiency improvements. You can see the numbers over here, 257x over a CPU and 30x over a GPU on these operations themselves. And in real-world applications, you get significant performance energy efficiency improvements as well. I'll let you read the paper. There's a lot more interesting things over here than we have time for. But this is an interesting area of research also. How do we take advantage of the processing using DRAM substrate and make it easily programmable, exploitable to the user, and make it more powerful. So talking about making it more powerful, some operations are very difficult to implement using this bitwise substrate. So for example, if you want to do a very complex convolution, for example, or a very complex multiplication or division, it may make sense to actually use lookup tables. And we have actually developed this Pluto system, which changes the DRAM a little bit more so that you can actually do lookup table-based computation. I will encourage you to take a look at it. This is completely artifact evaluated and online, so you can actually play with the code as well. Now, before I take questions, I will mention a couple of other things, and then before we move to processing near memory, I will probably take questions. Let me talk about what else can you do in DRAM. Basically, in DRAM, in existing DRAM chips, you can implement physical unclonable functions. What does this mean? These are essentially device identifiers. You can identify a device based on a signature of the device. So in DRAM, we have shown in this paper that if you violate the timing parameters, if you use some timing such that the circuits don't stabilize yet, some cells that are distributed across the DRAM chip form a signature of the device. It's unique to the device. So you can use this for remote attestation, for example, of devices. That's what physical unclonable functions are used. They're a basic security primitive. And on top of this, you can actually generate random numbers very efficiently inside the DRAM chip. If you actually, some cells, if you violate the timing parameters, we've shown with real experiments on real DRAM chips that some cells are great random number generators, meaning they fail at 50% probability. So if you access that cell with a reduced latency, you will get a true random number because of the physical processes that happen inside the DRAM chip. And this is fascinating also. This is actually very useful for offloading security applications to the DRAM. If you're interested, you can take a look at it. And we've shown that actually you can actually have other mechanisms that are even higher performance, true random number generation in DRAM. I will not talk about the details of it, but you can read papers. And you need end-to-end system designs to take advantage of these true random number generators. Okay, let me talk about flash and emerging memory technologies, and then I will take some questions. So flash is also capable of this sort of bulk bitwise execution. Flash memory is used in many devices that we have today. In this paper, we show that you could actually do this operation reliably on real flash devices, just like in real DRAM devices. Real flash devices are easier to do this because you actually have a programming interface to the flash memory if you actually are exposed to that interface. So basically, in this work, we enable in-flash multi-operand bulk bitwise operations with a single sensing operation with high reliability, and we see significant performance and energy efficiency improvements, as you can see. And this requires low cost, and it requires no changes to the flash cell arrays themselves. Let me give you the high-level idea. Basically, assume that you have 32 operands, 32 rows in flash chip over here. What we are able to do is concurrently enable those 32 rows. And if you concurrently activate those 32 rows in a flash block, what you get is a 32-bit input block bitwise end function. This is very fast, and it's 32 inputs. So it's actually a very large reduction of data. So in this sense, flash memory chips are actually much more capable than DRAM chips. Okay, I will not go into a lot more detail, but you could do this reliably. Now, let me give you why this happens. So these are 4 rows in flash. We are focusing on, again, 4 bits over here as opposed to the 16 kilobyte over here. If you simultaneously activate these 4 rows, you get the bitwise AND function. Why? Because the bit line itself reads as 1 only when all of the target cells store 1, because of the operational principles, analog operational principles of flash memory cells. And this is equivalent to the bitwise AND, clearly. Now, this is nice. And we show that you could actually go up to 48 inputs with this one. Bitwise OR is actually similar, except if you actually simultaneously activate multiple word lines in different blocks, you get the bitwise OR. Why? Because a bit line reads as 0 only when all the target cells store 0. Because it's an OR function, they actually drive another bit line over here. So this is a bitwise OR. Now, this is good also. Now, on top of this, you can have an inverse read function that already exists in flash devices today. So this is already functionally complete. You have a NOT function and an OR function and an AND function. So you're functionally complete. The same things that I just said for DRAM also apply over here. You should be able to port any algorithm to this device. And we show XOR, XNOR, etc. And this is the paper. You can find this information. If people are interested in developing this, we'd be happy to help. And we characterize real devices. And we see that you can have many operands in AND and OR with very small increase in latency. And we can actually make this reliable. We observe no bit error rates in the tested flash cells. Now, we simulate to actually get application level improvements. And as I said, you get significant performance improvements, energy efficiency improvements on k-means clustering, for example, or image segmentation, etc. And the larger the number of operands you have, the larger the data that you're operating on, the higher the performance and energy benefits. Okay, so that was Flash. Again, this is good. You can do this in DRAM and Flash. You can also do this on emerging memory technologies like phase change memory. This paper talks about how to do bulk bitwise operations like RowClone and mbit type of operations on emerging memory technologies in PCM and RRAM. And there's a whole lot of literature on this topic also that shows that in crossbar array-based memories, you can do matrix vector multiplication. We also have some work on that topic, including in Micro 2023 and Micro 2022. You can take a look at that tries to make things much more reliable in genomic systems. But these are some of the early papers that talk about how to use RRAM, for example, to do matrix vector multiplication, analog matrix vector multiplication based on Kirchhoff's laws. And this is clearly very useful for machine learning, as well as genomics and other workloads like graph processing as well. Okay, so that was kind of a discussion of how to do processing using memory. At this point, I'm going to switch gears to processing near memory, but this is a great time to take more questions if they exist.
Okay, so we actually have 2 or 3 questions. The first question is from Hisham. He wants to know whether it's possible to have access to the slides.
Okay, absolutely, yes. I will upload them to my website, but it may take a while until I upload them. But I can also send you the slides, Ramzi. If there's a place you can upload, or at least I can upload them and send you the link so that you can share where the slides are.
Okay, so the next question is from Marwan. He wants to know, based on Flynn classification, how can we classify memory-centric computers?
Okay, I mean, this is a great question. Basically, I would say that Flynn's classification is more about instructions and data and how they merge each other. In that sense, memory-centric computers also are part of Flynn's classification. They could be SIMD architectures, they could be MIMD architectures. But for example, what I showed you over here, there's a reason why we called, actually, if I go back over here, there's a reason why we call the SIMD RAM, because this particular style of computation using DRAM is bulk bitwise SIMD, single instruction, multiple data, where a single instruction operates on multiple bits. Essentially, columns are data, and a single operation does operations on columns. So this particular style is SIMD, but we have a paper coming up at HPCA where you can actually do MIMD, multiple instruction, multiple data, concurrently across different subarrays in DRAM also. So Flynn's taxonomy is very general. It's applicable to both processor-centric and memory-centric systems. So if someone comes up with a systolic array-based in-memory or near-memory computing engine, as I will talk about later on, that could be classified as, for example, MISD, multiple instruction, single data type of system. So that's a very good question.
Okay, so the next question is, how to deal with the challenge of verifying the correctness of memory-centric algorithms? Does that open the door for a new theory of computation?
Yeah, I mean, that's a good question also. So certainly there are several issues over here in terms of correctness, right? One is correctness from an algorithmic perspective, whether they actually produce the result you want from a functional perspective. And I agree that in this case, we really need to hopefully come up with a better theory of algorithms that is more data-centric. For example, when we were developing algorithms for SIMD-RAM or mbit type of substrate, there's no theory that would help you. You need to really rethink your application and make sure it's correct. But I think this opens up a new theory also that's much needed. But there's another aspect of correctness, which stems from the reliability of the devices. And in this case, that's a hard, I don't want to say harder problem to solve. Essentially, analog operation always has some noise, and this noise leads to some reliability issues. Ideally, you should eliminate this noise and not expose it to the programmer. But I think it will take some time to get there. So at some point, maybe this will need to be exposed to the higher levels of the software stack, such that the higher levels of the software stack will take this inherently noisy nature of analog computation into account and design algorithms and software such that in the end you get correct results, right? Despite the unreliable substrate. I don't want to call this necessarily approximate computing. Basically, I think of this as using unreliable substrates, analog substrates for computation, it could be used for applications that can be approximate like neural networks. I think that there's actually a lot of potential synergy over here. In the SimDRAM paper, for example, we show how to accelerate neural networks, like binary neural networks, benefit a lot from this, especially if you're tolerant to noise. But I believe that actually there needs to be some algorithmic work, software work, as well as hardware work, so that you can actually use unreliable substrate for reliable computation as well.
Okay, so you can continue. That's all we have.
Okay, wonderful. So there are a lot of good questions, so I'll keep them coming. Okay, now I'm going to switch gears. So I talked about processing using memory, which opens up a fundamentally different way of computation without adding logic to memory. Now we're going to talk about adding logic. If you add logic near memory, you can actually do anything, essentially. And this doesn't, in my opinion, require you to rethink a lot about how you do the computation, because it's computation as usual, except it's happening near memory. But I believe it still needs to enable us to think about what kind of computation should go near memory. How do we organize our applications such that we can take best advantage of near memory computation? And how do we program these systems? So I'm going to talk about these also. We're still going to talk about memory as an accelerator, except we're going to add logic near memory. And I think this sort of research and analysis is really important to do at an application level, meaning we take an important application and see how we can accelerate it near memory. So when we first started this research, we looked at graph analytics, for example. I'm going to talk about machine learning also a little bit later. But graph analytics is really interesting because graphs are clearly everywhere. They keep growing. Right now, there are people who are watching us on Facebook and LinkedIn, and these are graph-based models with many, many users. And scaling this to large scales, large graphs, and large computation nodes is challenging because they're essentially memory bound. So if you look at, for example, a very simple algorithm, PageRank, which is at the core of Google search, you have frequent random memory accesses and little amount of computation while you're traversing the graph, which means that this is very much memory bound. So we can actually execute a lot of these operations near memory. So when we first started looking at this, we were very interested in how do we actually execute operations near memory at high bandwidth and low latency and low energy. So we were actually very interested in 3D stacked memory technologies that are actually happening today. High bandwidth memory, for example, is becoming 3D stacked today. Hybrid memory cube, etc. I believe we're going to see a lot more 3D stacked memory technologies going into the future. So if you look at 3D stacked memory technologies, they stack logic layers to memory layers, and they have very high bandwidth, low latency connections between the logic layer to the memory layers, and also low energy. So we don't have extremely heavy interconnects, for example, like we have between memory and CPU in 2D systems, two-dimensional systems today. And there are other true three-dimensional technologies that are under development, like monolithic 3D, etc., that can combine things even at a more finer grain, as opposed to having still large through silicon vias. These works actually have vias that are much smaller, very similar to what we have in 2D today. So I think this space is going to change a lot going into the future, and there will be exciting opportunities. So, but what did we do in 2012, 2013? Essentially, we said that we're going to design, using 3D stacked memory plus logic chips, a graph processing accelerator. And we're going to take one chip, and we're going to connect it with many other chips, because clearly memory in one chip is not enough to house all of the graphs that we want to operate on. We're going to have a distributed system of these cubes, if you will. I'm going to call this a cube, and interconnect them in some way, and attach them to a host processor. And host processor will offload computation, graph computation, on this distributed system. And this distributed system will execute just like a GPU and return the results to the host processor. So what does this distributed system look like? It essentially, inside the logic layer of each cube, we have another distributed system, which is essentially an array of cores that are connected via some network. And these array of cores can do computation. But what we do in the system is essentially each core has ownership of memory in the stack on top of it. If one core wants to execute a function on a data item that belongs to some other core, that core needs to send a message to the core that owns that data. Essentially, we're not going to move the data. We're going to move functions to the data. So this is very similar to remote function call or remote procedure call based programming that's employed in distributed systems. Essentially, we have a distributed system where we're not going to move the data and use remote procedure calls. And ideally, you would like to partition the data such that you minimize the function call movement. So you do the functions locally. And if you do the functions within a cube, that's also not that costly. It's still within the chip. Now, hopefully, we will minimize the functions that are executed across the chips. So we do some graph partitioning such that the graphs are partitioned such that you localize computation as much as possible. That's the idea. So each of these cores are in order, so they're general purpose. They can actually be used for machine learning also, but you can also have accelerators inside them. We did not look at that in this particular paper, but later papers actually looked at them. And you do message passing. Essentially, you have a message passing to a system that uses remote function calls, and we have some prefetching mechanisms that enable higher bandwidth utilization for the cores that I'm not going to talk about over here. So what did we evaluate? We actually evaluated many machine learning algorithms that I will mention later. These are the systems that we evaluated with. You can actually look at that. These systems are all compute-centric. You can see that processor and memory dichotomy is there. They're different from each other. And the maximum bandwidth you can supply to the processors is limited because of the two-dimensional structure. Tesseract, the system we designed, is very different. Basically, there's no processor and memory distinguished from each other because they're within the same cube, if you will. You just connect these cubes. It's a distributed system of cubes, essentially. And you can see that at the time, we have huge amounts of memory bandwidth that's available to all of the processors, 8 terabytes per second. So today, actually, technology has improved, so this number is actually at least an order of magnitude larger. Okay, so we ported a bunch of graph processing algorithms, including PageRank, and essentially compared to existing systems that I showed you earlier. And we showed essentially that with a lot of optimization, with all the optimizations that we do, you get 13 to 14x performance improvements, average across 5 graph processing algorithms. But you can see that here we rethink the entire system. We rethought the algorithms. We also rethought the programming model. We also rethought the hardware. So by changing a lot in the system, you get significant performance improvements. Now, later works actually showed that by doing better optimization, like graph partitioning, memory mapping, interrupt handling, etc., you get this number closer to 100x. That's fascinating, I think. And we also showed that you reduce the energy consumption by 8x. Again, later works show that by doing more optimization to what on top of what we have done, you get even more reduction in energy, closer to, again, 2 orders of magnitude. And again, this is the paper. If you're interested, you can take a look at it. This is one of the papers that was selected to a special retrospective issue in ISCA 50, which was held this year. So we also wrote a retrospective of this paper together with our collaborators. I think this is the sort of thing that is going to be more important going into the future. This is a processing near memory system, meaning that we actually add logic, right? Explicit logic, explicit computation, explicit cores in a logic layer near memory, right? It's not a processing using memory system like SIMDRAM or MBIT like we discussed. I believe this is easier to adopt, and a lot of the machine learning systems are actually adopting principles related to this in some form or shape. And you can find that information in the retrospective over here. Okay, feel free to stop me if there are questions. Otherwise, I'll just go through these different papers that do different example approaches. And then I'm going to talk about some adoption challenges, and I'm going to talk about real processing in memory, and then we're going to conclude.
Okay, so there are actually 2 or 3 questions. We're going to take them.
Sure.
Well, the first question is from Hisham. What are the limitations and challenges associated with the implementation of memory computing systems?
Yeah. So I'm going to talk about this in the adoption challenges, but essentially there are quite a few challenges. Programming is a big one. So this Tesseract work, for example, tackles the programming aspect of it. It's basically proposed a programming model that's based on distributed systems. But we're going to talk about programming later on. I think programming is a huge challenge. Certainly, there are other challenges like system-level challenges that we need to look into, like coherence. If you partition applications between processor and memory, you need to tackle coherence issues, virtual memory issues. So if you look at the Tesseract papers, we looked at it as an accelerator, like a GPU. So we kind of sidestep those challenges. Coherence doesn't exist. It's physically addressed. There's no virtual memory over here. But if you really want to be generally programmable, you will need to solve these challenges over here. And then there's also, if you do, for example, analog computation, there's a reliability challenges. I'm going to talk about these in a later slide. So hopefully maybe you'll ask the question if that is not completely answered.
Okay. So the next question is from Hisham. In case of unexpected power outage, how resilient are memory-centric systems in terms of data integrity and recovery?
Yeah, I mean, that's a great question also. This is an aspect that is not examined as much in memory-centric systems. So I don't know the exact answer to this question, but my gut feeling, my hunch is you can design a memory-centric system that is probably much more resilient than a CPU-centric system. Why? Because if you actually have a power outage and if you have data integrity mechanisms and recovery mechanisms integrated inside the memory chip, inside the stored chip, or near the memory chip, near the stored chip, you can handle those issues like resilience issues much more easily, in my opinion, as opposed to notifying a processor and the processor like flushing its caches and dealing with this far away from the data.
Okay, so the memory-centric computing is going to make it easier.
I believe so, yes. But research needs to be done to show that.
Okay, so the last question. How would 3D stacked logic memory be made more accessible to a wider range of users and applications beyond specialized high-performance computing domains?
Yeah, I mean, that's also a good question. And I think part of this is it's going to be expensive, essentially, right, initially. Like any other emerging technology, 3D stacked systems are still emerging, in my opinion, even though there are examples of it like HBM that already exists in GPUs, which is still expensive. But essentially, over time, in my opinion, these systems will get cheaper because we will figure out the manufacturing processes. We'll optimize the manufacturing processes. I don't think it'll happen overnight, unfortunately. As people develop better manufacturing processes and also better motivating applications such that these can be used and manufactured at a much larger scale than we have today, I think they're going to inherently become cheaper.
Okay, that's all we have.
Okay, wonderful. Again, feel free to stop me. I have a lot more slides than I think we have time for, but if we need to go over, I'm happy to go over. So feel free to stop me if needed. Okay, so let me give you another example from the storage domain. Storage is actually quite interesting today, and I mentioned that we work on genome sequence analysis. And again, machine learning is also interesting here. Graph processing is also interesting. I'm going to pick genome sequence analysis as an example, but you could apply some of these principles to machine learning as well. So what do we do today in storage? So you have to move the data from the storage system to the main memory, to the cache, to the computation unit, so that we can actually do computation. But actually, this is a lot more expensive to do the computation, to do the data movement from the storage to the main memory to the computation unit. So there's overhead in processing, clearly, that you have, but there's an even bigger overhead in data movement from storage. So essentially, compute-centric accelerators are designed on the processor side and even memory-centric accelerators on the memory side. Can we actually have accelerators on the storage side? That's the idea. Compute-centric accelerators or memory-centric accelerators on the memory side reduce the computation overhead and some data movement overhead over here, but they don't tackle the data movement overhead from the storage system, which is actually huge. And that's the idea over here. The idea is to have accelerators on the storage system that can do some filtering, such simple filtering, such that data movement to the main memory and to the computation unit reduces significantly. So the key idea over here is to filter simple computation such that only a very small amount of data that really requires sophisticated processing goes to the CPU or main memory. And again, I don't want to go into a lot of detail. What can you filter? This is very application specific. You need to examine your application and decide what needs to be operated on in the storage. In this case, we do approximate string matching in genome analysis. We can easily filter exactly matching reads that you have reads and you're comparing them to a reference genome. You can easily filter how they are, if they're exact matches, for example. And some non-matching reads are also easy to filter, although it's a little bit more expensive in terms of acceleration. So with a simple accelerator, you can actually reduce the data movement overhead significantly. And we show that you can get significant speed up and energy reduction at very low cost by doing this on essentially an SSD that's compatible with today's SSDs. So I think this is fascinating, and there's a lot more to do in this area. But I wanted to put in storage over here so that people don't forget the storage system. And then there's sensors also that we should not forget. So clearly, you can do computation across the system. And if you want to learn more, there's this paper that you can take a look at. Okay, so I will move on to the next paper unless you stop me, Ramzi. Let me tell you a little bit about the work we did with Google on reducing data movement overheads. This is, again, also using simple accelerating mechanisms, simple functions on the memory side. So if you remember the graph processing work that we did with Tesseract, it's rethinking the entire system, which may not be affordable. But identifying which functions should be offloaded to the memory side is a lot simpler to do, and it doesn't change the programming model significantly. So we were very interested in the consumer devices, and we wanted to analyze these workloads. As I mentioned, we showed that we analyzed these workloads, and we showed that significant amount of total system energy spent on data moment. And we wanted to offload computation to processing in memory, where we have compute units in the logic layer of 3D stacked DRAM chips. And the challenge here is you have limited area and energy budget. So we actually talk about this area and energy budget in the paper. I'm not going to talk about this in detail. But what enables us to do this simply is a second key observation. We found out a significant fraction of the data moment often comes from simple functions and applications. And you can actually design lightweight logic to implement simple functions in memory, like compression, decompression. You can execute these either in general purpose low power cores or small fixed function accelerators. In my opinion, you need to have both and also have some configurable logic. So in the end, I think accelerators on the PIM side need to be heterogeneous as well. And we show that by identifying these functions and offloading them, you can significantly improve energy and performance by more than 2x. This is not like 14x, like we discussed earlier, but this doesn't require a lot of changes to the system either. So with simple changes, you can get 2x of improvement. Let me give you a couple of examples of these functions. So machine learning inference, for example, we looked at the TensorFlow framework. TensorFlow framework, you actually have an inference that you're doing on the mobile side, and you go through a neural network. And we found out that most of the inference energy is spent on data moment. And most of that data moment comes from simple functions like packing and unpacking of data and quantization of data. And all inference systems actually have that today. You want to quantize the data so that you can actually reduce the amount of computation that you do on the data. And you want to pack and unpack data so that you can get better locality in your buffer or cache. And we see that you can accelerate these packing and unpacking and quantization operations with relatively low cost and get high performance energy improvements. So there are other functions that I don't talk about over here, but compression, decompression. For example, in video playback and capture, you do deblocking, filter, motion estimation. And this is showing energy. If you actually offload these functions from CPU to the processing in memory cores or accelerators, you get significant energy improvements, as you can see over here. So accelerators are even more efficient than cores, as you can see. And performance improvements are also similar. Simple general purpose cores are actually not so efficient. So accelerators actually buy you even more on the memory side over here. So this is the paper that talks about all of these. I went through this relatively quickly, but hopefully this gives you an idea of how you can identify functions and offload them. This requires a lot of manual effort from the programmer. Later, hopefully, if you have time, I'm going to talk about a way of a methodology of aiding the programmers to do this. And hopefully in the future, we will have compilers doing this. There actually works at HPCA this year and some other works that are coming up that develop compilation mechanisms and also automated tools to enable programmers to offload these functions. Initial works are, of course, hand-coded. So again, you can do a lot of other things. You can offload computation from a main GPU to simple GPUs in the logic layer of 3D processors. We did this work with NVIDIA, where we showed that you could actually design a compiler to do this. But if you design the compiler to operate on existing applications, the way we did it, at least, you don't get huge performance benefits. You get between 30 to 50%, which is not bad again. But by changing the way we program things, you can get even better, in our opinion. We have other works that talk about how to schedule computation on GPUs with processing in memory capabilities. We have other works that talk about how to do pointer chasing, like linked list traversal or graph traversal with accelerators on the logic layer of 3D stacked memory. How to do actually better processing of cache misses on the memory controller side. How to do prefetching of cache misses on the memory side. How to accelerate stencil computation and weather prediction modeling using FPGA-based near memory architectures. And I mentioned how to do approximate string matching, sequence to graph mapping. I could keep going through all of this, but we don't have time. One thing I think that's very fascinating is time series analysis. Time series analysis, you're basically operating on huge amounts of time series of data, and you're trying to detect some patterns or anomalies. And time series analysis is used for this purpose. Machine learning can be used also for this purpose, and we can accelerate it significantly. Graph processing is actually still interesting. This paper actually shows how you can do this using set-centric architectures. Essentially, we're developing a set-based ISA, instruction set architecture, and we're doing graph mining on processing using memory as well as processing near memory architectures. Databases are another example. You can find that information. Again, these are all papers that are published at top venues that talk about how to accelerate computation in different sorts of applications. And I believe we need to do more of that. Now, in line with this AI Summit, let me talk a little bit more about neural network inference. And then I'm going to take a break to take questions. And then we're going to switch gear to near real processing in memory systems and adoption issues. But we also did this work with Google. And our idea was to identify neural network models and identify the bottlenecks in these neural network models and then accelerate them. So essentially, we analyzed 24 edge models in an edge TPU, edge machine learning accelerators, essentially, that are proprietary to Google. And we identified these compute-centric accelerators. This processor-centric accelerator actually is limited by memory, essentially. It operates at low throughput, low energy efficiency, and because it doesn't handle memory access as well. And we found out that this is because you don't have a data-centric accelerator. Essentially, different layers in neural networks require different treatment in terms of processing capability. Some of them need to be processed in a data-centric place. Some of them need to be processed in a processor-centric place. I'm going to give you an example. Essentially, we develop a framework here that consists of heterogeneous accelerators whose data flow and hardware can be specialized for specific families of layers. And I'm going to show you some results. We developed this three accelerator, or three heterogeneous accelerator, if you will. One is processor-centric, two of them are data-centric. And essentially, we can improve energy and performance by more than 3x at the same time. And we can also improve area efficiency compared to the baseline Google Edge TPU. So you actually improve performance, energy, and area all at the same time if you customize the system. I'm going to give you some examples. Basically, we've studied a lot of machine learning models from Google Edge models. We've looked at their parameter footprints, memory sizes, as well as arithmetic intensity, flops per byte. And there's a huge range over here, as you can see. Some convolutional neural networks have very little footprint and a very high arithmetic intensity, or they're very good for compute-centric accelerators. But some things like long short-term memories and transducers and increasingly transformer models have very little arithmetic intensity, but huge amounts of parameter footprints. So these cannot be treated the same way. That's our argument, essentially. There is a huge variation of layer characteristics across the models. And within a model, if you look at a single model, single convolutional neural network, for example, there's huge variation in terms of layer characteristics. If you look at different layers of a different neural network, this is a deep neural network that has different layers, there's a huge variation in terms of multiply and accumulate intensity, for example. That's true for this one also, and also for flop per byte, arithmetic intensity. So we need to design a system that can take into account this sort of differences across and within layers such that computation happens in the best fit hardware. And that's the idea over here. If you look at Edge TPU accelerator, regardless of the model and regardless of the layer of the model, a single monolithic accelerator executes it. And as a result, it's limited. What we propose is, based on the different models and layer, their runtime, a software runtime, which could also be hardware, we did software in this particular case, classifies the layers we're executing into the families. And different families have different sort of accelerators. For example, this family is compute-centric family, and it runs on a compute-centric accelerator. These other families run on data-centric accelerators near memory, as you can see. So we propose a specific instance of this architecture, but the methodology is general. It could be generalized to many different types of families. So how do you identify layer families? Basically, you need to group the layers based on their arithmetic intensity, footprint, and data reuse. And I'm not going to go through this, but essentially you do some clustering. And we find out that some of them are compute-centric and some of them are data-centric. You could actually go even more finer grain and for very different families, design very different accelerators as well. And when you actually design the accelerators, you also change the data flow. So the different designs that we have for different data-centric layers, memory-centric accelerators, essentially have different data flows also, because these neural networks have particular data flows. So I think there's a huge design space over here. Based on what we have done, you can actually design reconfigurable accelerators, etc. But we stopped at ASIC type of accelerators. Now, let me give you some results. Essentially, I'm going to focus on energy first. And if you look at over here to the left-hand side, this is actually very telling, I think. These are large-scale models, long short-term memories and transducers. In the baseline system, you see that most of the energy is spent on DRAM and off-chip interconnect, moving data and storing data, essentially, and accessing data. And if you actually add high bandwidth memory to the baseline system such that you alleviate some of the bandwidth bottleneck, you reduce the energy a little bit, but not too much. Now, if you do what we suggest, which is the Mensa architecture, then you actually get a huge reduction in energy, as you can see on these large-scale models. So this is actually the benefit that I see in machine learning, especially in these large-scale models. You can get huge benefits, and these large-scale models are dominated by data movement and data access, as you can see. Now, small-scale models or relatively smaller-scale models are also benefiting from what we do, but not as much. You can see that they're also bottlenecked by inefficiencies in the memory system, but not as much as these large-scale models. In the end, averaged across all of these, you get about 3x improvement in energy consumption and about 3x improvement in performance also. I'm not going to talk about performance as much, but the performance energy improvements are coming at the same time. Okay, if you're interested, there's a lot more in this paper where we talk about a lot of other optimizations, but we don't have time for that. Okay, so I think there's a lot more to do. We need to accelerate data-intensive workloads. We need to look at different types of processing in memory. In the end, we need to revisit the entire stack. And I believe we can get there step by step. And this particular paper covers a lot more. And we have written other papers also. Now, before I move to adoption challenges, I think we can take some questions over here. Are there questions?
Okay, so there are actually two interesting questions. Just a note before we take them. The time is yours, so we can extend the allowed time frame.
Okay.
We have more than 2 hours, so we can extend the time.
Okay, wonderful.
The first question is from Mohammed Al-Amin Boushusha. He's asking, how will this new huge research work about memory-centric computing affect the industry of computing hardware like big tech companies? And can small startups join such a new revolution? If so, how is that possible?
Now, that's an excellent question. I think what I'm going to cover next is going to answer some of these, but just to give you an idea of essentially large companies are very interested and they're developing architectures right now. Of course, a lot of the challenges that I'm going to describe next need to be solved still. But the good news is large companies like Samsung, Hynix, Alibaba are quite interested, and they're actually developing chips. On the startup side, I think there's a huge opportunity also, especially in emerging memory technologies like RRAM, for example. People are developing startups that can do machine learning acceleration, especially, or other data-intensive acceleration. I'm going to mention some of them. And the UpMem company, for example, the first company that has developed an in-DRAM near memory processor, they are actually a startup. They're still a startup. Of course, the startups have always this tension, right? You need to either succeed as a startup and sell your products, or you need to get bought in a nice way by some other company and then not get destroyed by that company later, of course, so that you can actually impact something. So I think there are opportunities in both large companies as well as startups, and I think that's happening in industry. I believe that there needs to be more that's happening. So there, in my opinion, this is a very bright time for having impact on fundamentally changing the computing systems that we have today.
Good. So next question is about different strategies to ensure stability and performance in memory-centric systems during updates, maintenance, in dynamic environments.
Okay, I'm not fully understanding the question. It's very general.
Okay. So shall I repeat it?
Yeah, if you could repeat it, that'd be great, and then I'll answer the way I understand it.
Okay, no problem. So he's asking about different strategies to ensure stability and performance in memory-centric systems during updates, maintenance, in dynamic environments.
I see. I mean, I think, okay, that's a good question, but I think that question applies to compute-centric systems also, right? Whenever you have a dynamic environment or updates or some unpredictability for some reason, existing systems have some adaptability, but unfortunately they're limited existing systems, right? They get disrupted, for example, during those updates, like if you run out of power, for example. I think you have similar issues in processor-centric systems. In my opinion, the question is not specific to memory-centric systems. I think we need to do better in all of those to design predictable systems. In fact, designing much more predictable systems is a whole area of research. Now, how does memory-centric change this design of predictable systems? That's a good question. And I don't know if I have put enough thought into this topic at this point. In my opinion, again, predictability is always better if you can reduce the latencies and reduce the energy. So fundamentally, again, with my gut feeling, I would say memory-centric or data-centric systems are reducing the energy and latency significantly. So fundamentally, they should be more predictable. Or at least the predictable issues, like mentioned, should be handled more easily in memory-centric systems. But again, how to do that exactly is an area of research, and it needs to be investigated empirically.
Thank you so much. So you can proceed with the next section.
Okay, great. I mean, these are very good questions, so I'll keep them coming. Okay, now we're going to take another switch of gears. I've talked about processing using memory. I've talked about processing near memory. I said that these need to be combined, and there need to be more works coming for combining them. Actually, we're looking into that, and we encourage other people to look at that also. Now let's talk about adoption a little bit. So clearly, this is a new paradigm, processing using memory being an even newer paradigm than processing near memory. So how do we adopt this paradigm? And actually, whenever you have new hardware or new paradigm, this is the most difficult question, in my opinion. You can design any kind of hardware, in my opinion, a lot of fancy hardware, emerging hardware, analog hardware. But if someone in the world, or most people in the world, or the key people in the world cannot program it, then you have a problem, right? This hardware can go wasted. And that has happened in the past for hardware, for example. IBM Cell is a great example. IBM Cell is essentially what you call an initial GPU at the time, but it didn't have some characteristics that are good for programmers, like coherence at the time. So unfortunately, even though it was used in Sony PlayStation, it didn't continue as much. So it was very hard to program at the time. Maybe it was also a little bit ahead of its time, and it was not marketed in the best way. Basically, I think there are a lot of issues over here that enable adoption of emerging paradigms. So I think these are some examples of potential barriers to adoption. I think applications of software, these are critical. That's why we've been examining a lot of applications, a lot of software, and how to take advantage of PIM. Ease of programming is similarly critical. How do we design interface and compile and hardware support to make it easy for people to take advantage of this sort of substrates, processing using memory, processing near memory? I think this is critical. I'm going to mention some works, but I'm not going to go into detail on this one. How to aid the programmer to identify which functions should be executed where. Again, these are issues that exist in processor-centric systems, but memory-centric systems take it to another level. Today, you partition your programs between CPU and GPU, for example. But what if you have CPU, GPU, machine learning accelerator, and also data-centric accelerators on the memory side? System and security support. How do you handle coherence? How do you handle synchronization? How do you handle virtual memory, which is a very hairy topic? How do you handle isolation? How do we design communication interfaces? So I think there are a lot of interesting things over here. So people are tackling this slowly, but research needs to be done more in these areas. For example, I mentioned the CXL interface, Compute Express Link. This is actually a very good move on the industry side to enable computation on the memory side or the storage side or any other device that uses the CXL interface essentially. So we have actually movement on the industry side that is good on the communication interfaces aspect. How to design the runtime and compilation systems? Because programming is not enough. If you need to adapt dynamically, I think you need to have a good runtime. Compilers are important also to enable this. How do you do the data mapping on the memory side, for example? Today's data mapping mechanisms are, for example, they all assume that CPU needs to access, or GPU or FPGA or whatever compute units. It's very compute-centric, basically. It's very processor-centric. They all assume that highest bandwidth should be provided to some processor that's accessing the memory. So it's a very, very processor-centric viewpoint. If you actually have processors near the memory or inside the memory, this data mapping needs to completely change, because now you have parallel execution across memory arrays, and your data mapping should not provide the highest bandwidth outside of the memory chip, but it should really be designed to provide high bandwidth to these memory arrays or processors inside the memory. And then we also need to develop infrastructures to assess benefits of this and feasibility of processing in memory and processing near memory system. And there's a lot to do over here. So hopefully I've covered a lot. I think there's a lot to do. I'm going to go show you some examples also relatively quickly. But in my opinion, the most important thing is our mindset. So if you think about the way computing has grown it's very processor-centric. It's ingrained in every single decision that we make in our systems, including, as I said, the theoretical aspects of computing, theoretical analysis, theory of computing, essentially. So, so when you examine something, in my opinion, you need to rethink the mindset so that the mindset is very data-centric. We should not, in my opinion, say, oh, this is the way things are done, so we should continue doing the things the way they're done. We should really challenge everything and say, how do we do it in a better way if you want to minimize data movement, for example? If you want to, if the data is the most important thing and we want to minimize data accesses and data movement and optimize for energy efficiency. So this is the most important thing, in my opinion, the mindset. Once you change the mindset, I think everything will come. Okay, so as I said, I think eventually we need to revisit the entire stack, but we can get there step by step. And I showed you some examples of step by step, offloading simple functions, for example, doing data copy and initialization using processing using DRAM. So I will not go into a lot of detail over here, but I will flash some papers. So we need to keep it simple. So some works that we have done targeted keeping it simple. For example, that's why we developed PIM-enabled instructions. The idea over here is you don't change the sequential execution model. You incorporate near memory processing capable instructions in the instruction set architecture. And these instructions are not too capable, but that can enable you some offloading to the memory side. If you're interested, you can take a look at this paper. And actually, SimDRAM work takes advantage of this PIM-enabled instruction concept. So going forward, I think PIM-enabled instructions are going to be even more important, in my opinion. A single instruction can unleash huge amounts of data parallel work on the memory side. So don't think of the instruction as a simple instruction that can do very little, but we're thinking about a simple instruction that can unleash huge amounts of work on the memory side, either in SIMD style or MIMD style. How do you use programmability? These are some recent papers that we have presented. I will not go into a lot of detail, but we need to come up with frameworks, data parallel frameworks, for example. And this is a paper that we presented at PACT that uses high-level primitives like map and reduce, etc., and adapts them to processing in memory. If people are interested in the software side, this is a very good place to start. And the source code is also available online, so you can actually use that to program UpMem systems, for example, but this could be adapted to other systems as well. How do you maintain coherence? It's a very tough area. I think if you want to partition an application between the processor and near memory processor, let's say, you actually need to maintain coherence, and this is not easy. And we show this in our papers. Traditional coherence mechanisms don't work well. They sometimes reduce performance, actually. Whereas ideal coherence mechanisms, actually, if you eliminate coherence, that's great. So we propose some mechanisms to do this coherence efficiently. And this is one latest paper that I know of on the topic. If people are interested, this is an area ripe for research. It's not an easy area, but I think it's a fascinating area. How do we... essentially, coherence problem is if memory is operating on some data and the processor is operating on the same data, how do they actually make sure the data is consistent across these different processors that cache the data, right? And if you actually want to satisfy the coherence, you should be satisfying the coherence in a way that minimizes the communication. And that's the challenge over here. How do you minimize communication to support coherence? How do you support synchronization primitives? This is a paper that we have published at HPCA. People can take a look at it. We need synchronization libraries to enable parallel processing in near data processing architectures. How do you support virtual memory? I think this is one of the tough questions because virtual memory requires translation. And with huge memory sizes today, virtual memory itself is hitting its limits. So there's a lot of inefficiency in the virtual memory system. In fact, we presented 2 papers at Micro 2023 in October, where we showed that you could actually optimize the virtual memory of existing processor-centric designs significantly by rethinking them in different ways. But once you go into near memory processing, the problem becomes, how does the near memory processor do address translation, for example? What parts of the memory system, virtual memory, can it access and can it not access? There are a lot of interesting questions over here, but I think virtual memory system needs to be rethought completely going into the future. Now that I've discussed some of the adoption barriers, let me discuss some real-world examples that I mentioned earlier. As I said, if I was giving this talk 1 year ago, or even 2 years ago, 5 years ago, most of these wouldn't exist over here. So today, we have actually a lot of interest in industry and real chips that are manufactured by industry. Some of these chips you can actually buy and do experiments on. Some of these chips you cannot because they're actually doing it developing it internally. And there are many startups that are actually doing things, as I mentioned also. And then there are CXL-based solutions. This Compute Express Link enables people to offload. So in this particular case, for example, there's a card. And in this card, the host CPU uses a CXL protocol to offload computation. And I believe they show a database application over here. This card is an FPGA. And then the database application can be accelerated using this FPGA, using the CXL interface. So this is a processing near memory solution. It's a step in the right direction, basically. Samsung also has similar things. And more recently, these companies, SK Hynix and Samsung, I don't have them here, but in some conferences, Open Compute Summit, for example, they've shown at a high level that they could accelerate large language models using the CXL processing near memory architectures that they have. And I believe that actually this is actually very promising because it can enable near memory processing across very large amounts of memory. This is clearly not the final solution, but this is a step in the right direction. Again, if you're interested in real processing in memory, we have a bunch of tutorials that I will mention over here again. Let me talk a little bit about this startup, UpMem startup, which is the first startup that has actually came up with these chips, or first company that has came up with these DRAM chips. And these DRAM chips have processors inside them, basically. These are standard modules that you can plug in to a processor. You can buy it also, etc., from them. Essentially, they have these processors called DPUs, DRAM processing units. They operate at relatively low frequency because they are implemented in the DRAM process, not logic process. That's fine. And you can have systems that have 2,560 DRAM processing units. And we write papers about it. If you want to be initiated, you can actually take a look at these papers. So these are real systems. That's fascinating. That's nice. What does the processor look like? Essentially, next to each DRAM bank in a DRAM chip, they have a general purpose processor. This is a multiple instruction, multiple data processor in Flynn's terminology that was mentioned earlier. It's a multi-threaded processor, essentially, and you can program it nicely. It has an instruction cache and a data cache, essentially. It's very similar to an existing fine-grained multi-threaded processor with caches. So now you can do near memory processing in this processor. It has a lot of idiosyncrasies that I'm not going to go into. It's not perfect, clearly. It cannot do very heavy multiplication, for example. But even with those downsides, you can still find applications that can be accelerated significantly. And we talk about a benchmark suite for it in this particular paper. Again, I will not spend a lot of time. You can actually read some papers, talk about, watch some lectures that we deliver, especially Juan from my group has delivered. This is a very good fit for workloads that are memory bound, that don't have a lot of arithmetic or operational intensity. So you need to find those workloads. And if you find those workloads, you can outperform existing CPUs and GPUs significantly, as you can see over here. So this is the DPUs, the red bars. These are the workloads that are a great fit. For example, histogram computation, vector addition, scanning through a database, etc. But there are some other workloads that are not good fits, at least in this particular system. And we also classify them as well and discuss them in the paper. A GPU is much better, for example, for some of these workloads because this particular processor was not designed for them. For example, some breadth-first search traverse is not very good because of some of the communication issues that exist in these processors. Okay, basically, for workloads that require simple operations or no arithmetic operations and little communication across the DPUs, this could be a good fit. But I believe this is just the first generation. This was, as I said, manufactured in 2019. I think future generations are going to be even better. And if you're interested, you can take a look at these papers. This is a shorter version that talk about this particular system and benchmarking of it. And we actually released the benchmarks. People have been adding to these benchmarks. So you can actually take a look at these and develop real benchmarks that could be run on real processing in memory architectures. You can find them here. Okay, and there are a lot of talks also. So I'm going to skip these. So a little bit more on this real system. You can do machine learning training. This is not optimized for deep neural networks because multiplication is not optimized. You can do 8-bit integer multiply. And if you want to do anything greater than that, unfortunately, you need to go through software and it's not very easy. So we look at more classical machine learning algorithms. And we show that if you optimize your classical machine learning algorithms like k-means clustering, decision trees, etc., you need to optimize your data representation. You need to use lookup tables. You need to optimize data placement and layout. And if you do all of these, you can actually outperform CPUs and GPUs significantly. So this is promising. Even on a system that cannot do very good multiplication, you can still improve performance over existing CPU and GPU. on classical machine learning. And if you want to learn more about that, Juan has talks on this topic. And we presented this paper at the ISPAS conference last year. We also have other analysis on the toughest part for this architecture, which is multiplication, essentially. If you're interested in this, you can take a look at the SparseP paper. Essentially, we look at how to optimize multiplication, essentially, on an architecture that cannot do multiplication really well. And we actually look at many different ways of doing compression, data types, data partitioning, synchronization, and load balancing. You can find all of these in the open source code. And there's a comprehensive analysis of how to do sparse matrix vector multiplication on this system. So in terms of efficiency of data movement versus computation, UpMem system is great for sparse matrix vector multiplication, essentially machine learning, I would say, because machine learning is really driven by sparse matrix vector multiplication. Efficiency is great, but peak performance or absolute performance is not great because multiplication primitive itself is not very good in UpMem. But if you actually design or redesign a near memory processing engine that can do very good multiplication, like other architectures that I'm going to talk about do, I think you can actually accelerate machine learning significantly. Okay, there's more on this topic, and you can find papers. There's other stuff that we have done that I'm not going to talk about, and you can actually do sequence alignment in these systems with higher performance than CPUs and GPUs. But I think that's all I'll talk about UpMem. Any questions so far? Otherwise, I'm going to switch to some of these other real memory processing systems, and then I'll conclude.
Okay. So this is just a thank you comment from Amin.
Okay, you're welcome.
Very interesting talk. Thank you so much, Professor. It's nearly 11 p.m. in Algeria, but we are enjoying every moment.
Okay, that's great to hear. And sorry for keeping you up late, but hopefully you had your dinner, and this is good after dinner discussion.
Yes, we actually did. Another question about, it's a general one, I think. It's from me. What's the optimal timing for initiating the standardization of a new technology, striking a balance that avoids premature stifling of innovations, yet prevents the risk of late standardization, leading to the monopolization by a single entity with the most significant technological advancements?
Yeah. I mean, that's an outstanding question, I think. I don't have a good answer, frankly, for that question. I'm not sure what's the optimal time, but everything that you said makes sense, basically. If you are able to standardize it in some way that enables innovation by many different people, hopefully you will have a lot of diversity in the ecosystem that everybody, most or people who are interested can contribute, right? But if that standardization is not good, meaning if the standards that you design is not taking advantage of the fundamental capabilities of the technology, then someone else may come up with a much better system that doesn't obey the standard, and they could still monopolize the system, right? So if you look at, for example, how things have evolved in GPUs, we see that, I think. Clearly, NVIDIA has an advantage because they have this closed source thing that's not standard, that many people cannot get into, right? I think, in my opinion, in processing near memory, we're not there yet. We still need to explore how things evolve and explore the fundamental limitations of the technology so that we can move to standardization. But I think people should also be talking about how to move forward with standardization. So there should be a concurrent effort with research that's happening in industry for standardization. So in this sense, I think Compute Express Link, CXL, despite all of its shortcomings, it's still a good step in the right direction. Hopefully, it will be adopted by a lot of players in industry so that at least we can enable some near-memory computation, right? And over time, that standard can be made better, hopefully. Right?
Okay. So last question before we move on. Can we say that parallelism and determinism are the only driving forces advancing computer architecture?
Parallelism and determinism, you said?
Yes.
Okay. I'm not sure. I mean, parallelism is certainly important. I wouldn't say it's the only force because, I mean, there has been a lot of work that has been done for energy efficiency, for example, right? And it's not necessarily taking advantage of parallelism. In this case, processing near memory, you're taking advantage of parallelism and energy efficiency improvements at the same time. But I wouldn't say they're the only forces. I think there's a lot that happens on the memory system design, for example, that doesn't necessarily take advantage of parallelism or determinism. I mean, determinism is useful, but I'm not sure if it's really necessary for everything that we do. For example, if you do some if you think about, for example, how computation is done, perhaps in the brain, right? I don't claim to understand this, but there's a lot of stochastic computation, right? And I'm not sure if determinism is really needed in the systems that we build going into the future. Some applications will definitely need it, but maybe we should really be rethinking our applications so that we can take advantage of the underlying parallelism. Parallelism is there, but maybe in a way that's not necessarily completely deterministic, right? And a lot of interactions that happen with the physical world, for example, is similar in that sense. And maybe the artificial intelligence also needs to be like that going into the future.
Okay, so that's all we have. We can continue now.
Okay, wonderful. Okay, so we've talked a lot about real systems. So let me give you a little bit more. I'm not going to go into detail, but I'm going to give you some more hope in terms of big players like Samsung actually introducing processing in memory architectures so that they can accelerate machine learning. So this is an HBM-based architecture. They call it function in memory DRAM. They could actually, essentially, it's designed for doing floating point multiplication addition. It's a very different design from the UpMem. UpMem is general purpose. It cannot do even integer multiplication. Well, forget about floating point. It cannot do any floating point at all. So you can see that this is designed as an accelerator that can do multiply and accumulate, which is at the core of machine learning. And you can read Samsung papers. You can see that they have a programmable computing unit on the DRAM chip. And this is the instruction set architecture that is used, that's exposed by that DRAM chip. So I will not go into a lot of detail, but this is real. And Samsung has been writing papers about it. So I think this is a step in the right direction also. This is very good for machine learning acceleration. And more recently, Samsung and SK Hynix, using similar chips, they've demonstrated that large language models can be accelerated at high performance and high energy efficiency also. This is another system, very different, also developed by Samsung together with Meta. Here, they don't modify the DRAM chip. DRAM chips are DRAM chips, commodity DRAM chips, but they have a buffer chip over here, which is an FPGA. And in this FPGA, they implement primitives that can accelerate recommendation systems. So, and then they've written papers about it also that talk about the efficiency, etc. And these could be used in data centers, for example, to accelerate recommendations. SK Hynix introduced this accelerator in memory system, which is essentially somewhat similar to the Samsung system, but perhaps it's more capable. It's GDDR, graphics DDR-based. Essentially, it can also do matrix vector multiplication, multiply and accumulates very well. And if you're interested in this, there are papers on this topic. I kind of mentioned them. For example, I put it over here. And there are also talks on this topic in the real processing in memory symposium that we had. We actually had talks from Samsung, SK Hynix, IBM, etc., that talk about these architectures that they've been developing, including Alibaba. That's the next thing I mentioned. Alibaba also modified the DRAM chips. This is the major circuits conference also. And they basically shown that they can accelerate recommendation inference using specialized logic on a DRAM chip. In this particular case, I think it's, it's again a 3D stack chip. So people are working on it, and these major companies are actually investing in it, as you can see. And I already mentioned this more recently. CXL interface has enabled some more innovation on the memory side, and major manufacturers are looking into it. So the good thing is we're having processing in memory in the real world, as you can see. So adoption barriers are slowly being eliminated, hopefully. But we also need to do more research and development to make it even more adoptable. So one thing I will mention quickly, because people can use it in their research also, we've developed this DAMU analysis methodology and workloads where we ask the question, when should we employ near data processing? Essentially, there are all these works that showed great results, but whenever a programmer or an application developer is faced with the question of what should I employ near data, what should I ship to the near memory processor, they need to analyze their workload and analyze their function. So we wanted to ease this development. Basically, in this work, we analyzed 345 applications from many distinct domains, as you can see. You can find the full list in the paper. And we basically classify these functions from these applications into 6 different memory bottleneck classes. So the function may be bottlenecked by DRAM bandwidth, DRAM latency, L1 and L2 cache capacity, L3 cache contention, L1 cache capacity, etc. Or it could be compute bound. I think one of them should be L3 cache capacity over here, but yeah, that needs to be fixed. But basically, you can use our methodology to identify functions and classify them to different bottleneck classes. And different bottleneck classes behave differently in terms of whether they should be executed in a near memory processor or not. Of course, this depends on the near memory processor as well. So for example, if a function is compute bound, it should not be shipped to the near memory processor. If a function is DRAM bandwidth bound, we show under what conditions it should be shipped to the near memory processor, etc. And this is a classification methodology. So I don't want to go through this in detail, but again, this is all open source, and you can find a lot of information on this topic, and you can use this. We also have a simulator to simulate near memory processing engines. Okay, and then there are talks and papers on this topic also. I already mentioned this, but there are some other recent papers. Like I mentioned, programming is important. We've been looking at homomorphic encryption, which is actually really important for security in the future, and how to accelerate it using real processing in memory systems. You can take a look at that. And again, near cache processing is also interesting, and there's a lot of work in this area that I don't have time to talk about. One thing I will mention is there's a lot of infrastructure today. If you want to get into this research, clearly there are real systems. If you don't have access to real systems, there are simulators. And more recently, we released a Ramulator 2 simulator that can be adapted for PIM systems. And in fact, people have already adapted this to processing in memory systems in papers that are coming up in the future. So this is where I'm about to conclude. Let me conclude, and if there are questions, I will take more. Okay, basically, I think we need fundamentally energy-efficient architectures. And those architectures, I believe, have to be data-centric. We also want fundamentally high-performance architectures. I think those architectures need to be data-centric. I think if you change that fundamentally X to sustainability, security, etc., I believe we will find those architectures need to be data-centric, which is exactly the opposite of what we're doing in our systems today. Our systems are processor-centric, computation-centric, as opposed to data-centric. So I think we have a huge challenge and opportunity for the future. We need computing architectures with minimal data moment that are data-centric. So let me conclude. I believe we must design systems to be balanced, high-performance, energy-efficient, and we want all of them at the same time. This will hopefully lead us to much more intelligent systems going into the future. And I outlined a vision where we design systems that are data-centric, data-driven, and data-aware. I did not talk about the data-driven and data-aware part as much, but we focused on the data-centric part. But I believe data-driven and data-aware are actually part of the equation, larger equation, and these are synergistic with each other. In all of these, I believe we need to enable computation capability inside and close to memory, and essentially anywhere else where data is stored or generated. I believe this can lead to orders of magnitude improvements, and I've given you some empirical evidence in the field from both real systems as well as simulated systems for this. And I believe going into the future with creative thinking and better engineering, we can do even better. Hopefully, this can enable new applications and computing platforms. Genomics, for example, I think is an area that's ripe for this sort of platforms, but machine learning also, in my opinion. Even machine learning platforms today that we use are mostly processor-centric. They can benefit greatly from data-centric platforms, as we have discussed. This could also enable a better understanding of nature, in my opinion. So in psychology, for example, I have a degree in psychology in my undergraduate, in addition to computer engineering. So while I was studying psychology, psychologists are fascinated by computers. They were basically trying to use computing as a paradigm to understand humans. And I think this was terrible. This really fell apart. Because computers have almost no resemblance to humans in the way they process things. So I think if we actually design systems that are more resembling how nature processes things, we can probably have a better understanding of the nature as well. And these things could be synergistic with each other. And who knows what else. So I believe future of truly memory-centric computing is bright, but we do need to do a lot more research and design across the computing stack. The good news is, I think a lot of people in industry are now interested in it. So there could be a potential for huge impact that could potentially be immediate also. So I believe we need architectures that are fundamentally better. And I like using this picture. So if I look at this picture, there's clearly a lot of computation going on in our brains, for example. That's one of the nature's computing devices that exist. I don't think we quite understand it yet. But the principles that are employed by this thing over here are very different from what we do today, in my opinion, especially with regards to how we process data, how we move the data versus how this thing doesn't move the data, perhaps. We don't quite understand it yet. I think we need to understand it more. But again, to be able to get to something like this, we need to revisit the entire stack. So there are some good principles that I'm going to skip over here. More than anything else, we need open minds. And I will mention these papers. I will mention people who funded our research. And most importantly, this is very important because I'm presenting the research that has been done by my group, and my group is relatively large. And there are a lot of people over more than a decade who have contributed to this research. If you want to learn more about them, you can look at this webpage. We're always looking for good students, interns at all levels. If you're interested, let us know. And these are some faces that you can associate with the research that has been done. And you can take a look at our newsletters also that we released at different years if you want to learn more about the type of research that we've been doing. And this is the most recent newsletter and most recent incarnation of the group at the time. You can look at those newsletters to learn more about our research. And if you want to learn more about an introduction to other research that we do, you can also take a look at the YouTube videos, etc. And you can find more information about our people, PhD and postdoc alumni. These are an incomplete list of PhD and postdoc alumni, and then we have a master's and bachelor's alumni also. And these are some of the awards that they've won. So, okay, I will almost end here, but if you want to find the papers, talks, and artifacts, etc., you can find them on my website, on the YouTube channel, on the GitHub. I will mention GitHub. I think we're doing a lot of open source development. I really believe that open source is extremely important for fast progress and also progress in the entire world as opposed to closed source development. So you can find our open source tools on the GitHub. As I mentioned, there are a lot of other material that we have. I will leave these slides over here. You can find our courses, etc. But I'm going to conclude over here with the last slide over here. Now I can take more questions if people are not in bed yet.
Well, thank you so much for your talk. That was actually very enlightening. You've actually opened our minds towards many research opportunities to explore. Thank you. So we're going to take a couple of questions before ending. The first question is from Marwan. He's asking about the relation between memory-centric computing and neuromorphic computing.
Okay, great. I was expecting this question. And that's an excellent question. In the end, I believe, so neuromorphic computing, at least the way it's understood so far in the most general sense, is imitating the neurons, right? That's the idea, basically. You imitate some spiking functionality in the neurons, and you do computation based on that. So fundamentally, that's memory-centric, because neuron has some information stored in it, and then you basically do the computation locally in the neuron based on a model of the neuron, which I believe may not be completely accurate based on what we know, but at least it's a model of the neuron. So in my opinion, neuromorphic computing is actually a type of memory-centric computing that is more similar to processing using memory, but I don't want to call it necessarily that. Essentially, you're using the analog operational properties of a device to imitate a neuron, right? And there's work, for example, at IBM that has used phase change memory devices, the analog operational properties of phase change memory devices to imitate spiking neurons. This was actually discussed by Abu Sebastian and I think Manuel de Gallo in our 2 real processing in memory sessions. So you can find this information in our real processing in memory sessions. So in that sense, I think neuromorphic memory is a subset of the memory-centric computing, but I believe memory-centric computing and data-centric computing is greater than neuromorphic computing.
Okay. Another question, it's coming from me. Is adopting the data-centric paradigm the final solution? Or we might face other problems that are not currently visible to us as we move in time?
Yeah, I mean, that's an excellent question. We should always be open-minded, in my opinion. I'm not claiming that this is a final solution. I think these different paradigms need to coexist. I think today we have the compute-centric paradigm. I'm not suggesting that that should go away. I think we should do things compute-centric when it makes sense to do so. And there are cases where you have extremely high locality, for example, and you can fit everything in your caches and you can blast through computation with a compute-centric paradigm. That should remain over there. But we should enable other paradigms like data-centric paradigms. Is there anything else beyond this? I don't know. I think people should explore. So I think in research and science, we should always be open-minded and we should always be asking these questions so that we can make better progress, right?
Okay. The last question, I think, it's from Amin. He's asking about the prerequisites for a student to join your research group for a final year internship project or even PhD in order to work on such a topic?
Okay, great. I mean, that's a great question. So essentially, I would say you need to learn, internship. Let's take internship because it's easier than a PhD, right? PhD requires a little bit more to be done. So for an internship, for example, you need to first apply. We have an application website. And in the application website, we ask you for like reviewing some of our papers. So there are no prerequisite, in my view, other than demonstrating to us that you can think critically, you can program, and you can actually learn and do significant research. Now, this is a bit nebulous, right? In the sense that we have an interview-based process. So that initially we evaluate your application based on, for example, how you evaluate the papers, what kind of ideas you generate from the papers. You should not have written a paper on your own. That's not a prerequisite. We don't require you to write papers. We just require you to be able to critically evaluate papers. And sometimes we ask for more papers. And we basically discuss those papers with you to see how you think, essentially. And we may actually have some programming questions to see how you can actually program, right? That's actually important for developing some of this research. So if you go and look at our application website, I don't know if I have these in the slides, backup slides maybe. Oh, there you go. I found it. I think this is our application website. It will ask you basically to upload your documents like transcripts, if you have test scores, although they're not as important in our opinion. You may have a not so great GPA, but you may have a good understanding of how a computing system operates, for example. So the most important thing is convincing us that you can actually critically think, develop some ideas, however small they may be, but show that there is a positive thing in the development of ideas direction, and you can program and you can learn a lot. So that happens through an interview process, fortunately or unfortunately. We don't look at really metrics, let's say. Yeah.
That's very interesting. This is the last question that just appeared in the comments.
Okay.
So Hisham is asking about how does the architecture of memory-centric computing systems facilitate scalability, partially when dealing with increasing workloads and growing data?
Okay. I mean, that's a great question. So this is actually a good thing for memory-centric systems, and that was our argument. So if you go through the Tesseract paper, for example, okay, if I can find the slides, there are a lot of slides, as you can see over here. If you go to Tesseract paper, that was our argument, basically. Our argument was that this sort of system is a lot more scalable than today's systems because you're growing computation together with the data. We call this the memory capacity scalable performance. So this is the system. Basically, as you grow the memory size, computation also grows in a scalable manner. So I think this is an example of memory-centric system. And I think memory-centric systems in general have this sort of behavior. Computation grows with the size of memory, essentially with the size of data. Today, what happens is you have computation units and you have memory. They're far away from each other and they're bottlenecked by some sort of interconnect in between. You can increase the memory size. You can increase the computation size, but you'll be bottlenecked by the memory bandwidth in between, right? And the latency and etc., energy, etc., all of those. Here, you're not bottlenecked by that bandwidth. As you grow the computation, as you grow the memory, the bandwidth also grows because you're adding more memory and memory bandwidth also together with computation and memory. So in that sense, memory-centric systems are fundamentally scalable. This applies to Tesseract. This also applies to SIMDRAM and bit. There we are exploiting bit-level parallelism in DRAM. If you add more subarrays, more arrays into DRAM, more DRAM chips, your bit-level parallelism is still growing, and computation capability is growing together with memory. And we show this in both Tesseract and MBIT papers that as memory sizes, as dataset sizes grow, the performance improvements also grow.
Thank you so much. I think that we're going to stop here. So again, Professor Onur Mutlu, thank you so much for your time. Thank you so much for your enlightening talk on memory-centric computing. Your clear explanations and illustrative examples have sparked a keen interest in this innovative field, expanding our understanding. I appreciate your insightful presentation, which has ignited a strong interest in this groundbreaking area. Thank you for opening our minds.
Okay, thank you very much, Ramzi, for inviting me, and thank you very much for all these questions. If people are interested further, they can contact me over email or LinkedIn. And if people are interested in internships, etc., they can certainly apply, as I discussed.
Okay, thank you.
And have a good night.
This is the end of today's talk. Make sure to not miss out our on-site event this Saturday, where we will have more exciting talks. We will be very happy to see you there. Take care.